Química de la UNAM. Démosle un fuerte aplauso. Asimismo, nos acompaña el doctor Omar Amador, quien él es la cabeza del Departamento de Sistemas de Medio Ambiente y Atmósfera, Tecnologías de la Atmósfera. Démosle un fuerte aplauso. Asimismo, contamos con la presencia del doctor Philip Marriott, desde Australia, quien él es un experto en la tecnología GCxGC y vamos a contar con su presencia. Un fuerte aplauso. Asimismo, por parte del Leco contamos con el doctor Alan Griffiths. Él es el líder global de las ciencias de separación para Leco. Y finalmente contamos con la presencia del licenciado Jorge Rodríguez, quien él es el director de Mercadotecnia de Leco Latinoamérica. Pues para dar un inicio formal a este evento, vamos a pedir la presencia del doctor Carlos Amador para que nos brinde unas palabras.
Muy buenos días. Good morning, everyone. Welcome to the Chemistry School. Welcome to UNAM. We are glad you are here. Buenos días a toda la gente que viene de visita a la Facultad de Química, a la Universidad Nacional Autónoma de México. Siempre nos da mucho gusto recibir a visitantes en nuestras instalaciones. Y sobre todo nos da gusto recibirlos para un evento como este. En particular por varias cosas, pero quiero irlas señalando. Una es que este evento está realizado en colaboración con el Instituto de Ciencias de la Atmósfera y siempre es un logro cuando las distintas entidades de la universidad se reúnen para coincidir sus experiencias, para sumar sus experiencias y sus habilidades en lo que tiene que ser la base de la ciencia moderna, esa combinación multidisciplinaria de nuestras especialidades respectivas. Pero luego se pone todavía más interesante un evento como el de hoy, porque estamos haciendo otra cosa, que es la colaboración con la industria química, la colaboración, la extensión de nuestros esfuerzos académicos para colaborar con la industria química y atender aplicaciones de nuevo modernas. Y todavía es una tercera cosa interesante, el hecho de que lo que estamos viendo aquí es las técnicas más modernas, las técnicas más avanzadas que nos pueden ayudar en los problemas que estamos enfrentando en general. Eso es quizá lo más importante. Si lo pensamos un segundo, vivimos una época especial, una época extraordinaria, en el sentido en que nunca habíamos tenido tanto conocimiento como tenemos ahora, nunca habíamos tenido tantas capacidades tecnológicas como tenemos ahora. Y eso es importante porque tampoco nunca habíamos tenido problemas tan serios como los que tenemos ahora. Habría que pensarlo filosóficamente si esas dos cosas están relacionadas, si el progreso en nuestra ciencia y en nuestra tecnología, como dicen algunos, está relacionado con los problemas a los que nos estamos enfrentando como resultado de eso mismo. Pero de todas maneras es interesante la situación en la que estamos porque, repito, nunca habíamos tenido problemas tan serios, pero nunca habíamos estado tan capacitados para resolverlos. ¿Quién va a ganar? Eso es lo interesante y eso es lo que estamos viendo a través del esfuerzo que hacemos en estas actividades académicas, en estas actividades económicas, en estas actividades industriales. Bienvenidos de nuevo a la Facultad de Química. Agradecen a los invitados la recepción por parte de la Facultad de Química y yo quisiera retribuir comparativamente diciendo agradecemos nosotros en la Facultad de Química la atención que ustedes nos prestan y la oportunidad que nos dan de mostrar nuestras capacidades y recibirlos en esta que es su casa. Muy buenos días.
Agradecemos las palabras del doctor Carlos Amador y en este momento le vamos a pedir al doctor Omar Amador que nos dé una pequeña semblanza de lo que va a ser este ciclo de actividades con un poco el esquema con el que vamos a estar trabajando. Muchísimas gracias.
Muy bien, pues bienvenidos, ya somos más, me da mucho gusto. Esta es su casa y la casa de muchos que hemos estudiado y pasado y tenemos buenos recuerdos, profesores de antaño muy respetables. Muchas gracias por estar acá. También las compañías que se han tomado el tiempo para estar con nosotros, las distintas secretarías gubernamentales son bienvenidos también. Y es un evento en el que es, digamos, único y pionero en su tipo, porque tenemos dos extraordinarias celebridades, digamos. El primero es el doctor Phil Marriott, que es un experto en la cromatografía de gases bidimensional, pionero en el desarrollo de tecnología avanzada para el análisis de mezclas complejas de distinta índole. Por eso la invitación es para distintas áreas, desde alimentos, petroquímica, perfumes, cosméticos, aire, agua, suelo, etcétera, etcétera, etcétera. Entonces nos va a dar una pequeña probada en estos 2 días de su experiencia y de la capacidad tecnológica que representa esta tecnología. ¿Y quién la vende, quién la ofrece, quién es el soporte, digamos, económico de este evento? Pues es Leco. Y queremos agradecer a la compañía pues sus atenciones y también el hecho de que haya destinado un presupuesto para este magno evento, que es gratuito para ustedes y para el crecimiento, digamos, profesional, la adquisición de conocimiento novedoso y de tecnología novedosa gracias a la compañía. Y los representantes que los iremos mencionando conforme vayan interviniendo. Entonces, las actividades son 2 días. Los lunes y martes, las actividades matutinas de 9 a 2 serán en este recinto, en la Facultad de Química. El primer día tendremos 4 sesiones y el segundo día el curso de bidimensional por el doctor Marriott. En la tarde habrá una sesión especial para aquellos interesados en conocer más sobre la tecnología y tener contacto más directo sobre sus aplicaciones. La pregunta es, ¿me sirve o no me sirve la tecnología para que yo la aplique en lo que hago? Esa es la pregunta principal. Esa sesión va a ser en el Instituto de Ciencias de la Atmósfera. Aquellos interesados pueden pasar a la mesa de registro pues para anotarse. Mañana en la tarde ofrecerá una última charla el doctor Marriott relacionada con el análisis de mezclas complejas ambientales, básicamente, y va a resaltar la importancia de 2 variables que caracterizan a la técnica, que es la selectividad y la sensibilidad. Entonces va a hablar, digamos, sobre estos aspectos que muchas veces no son conocidos o son poco valorados, entonces se van a resaltar. Esperamos contar con su ánimo, ¿verdad? Que no decaiga. En el transcurso de las sesiones, el staff, que son mis alumnos, van a estar atendiendo sus requerimientos, les van a estar orientando y les van a pasar unas papeletas, ¿sí? Por aquel que no se anime a hablar en inglés o en español o a hablar simplemente, entonces, por favor, el comentario o la pregunta en la papeleta. Y el ingeniero Felipe nos hará favor de ser el maestro de ceremonias, él va a tomar el tiempo, etcétera, y también va a hacer las preguntas. Entonces, siéntase en libertad de hacer las preguntas y comentarios que ustedes creen conveniente, ¿no? Y con toda confianza, el evento es para ustedes. ¿Sí? Bueno, entonces, pues bienvenidos al evento.
Muchas gracias, doctor Omar. Pues para seguir con el orden del Presidium, vamos a pedir al licenciado Jorge Rodríguez que nos dirija unas palabras a nombre de Leco Corporation y a nombre de Leco México.
Bueno, primero que todo les quiero agradecer a todos su participación el día de hoy y para mañana para esta conferencia. De parte de la corporación de Leco y el trabajo que hicimos en conjunto con ustedes de la UNAM, les agradecemos esta oportunidad de presentar este temario. Hemos traído especialistas para poder darles un conocimiento sobre la tecnología que produce Leco, pero reitero lo que dijo el doctor Amador, esta sesión es para ustedes. Les pedimos de que después de que los congresistas den su plática, que se esperen con sus preguntas, pero tomen la oportunidad de hacer las preguntas que tengan. Tenemos aquí personas con mucha experiencia y mucho conocimiento que puede que les puedan ayudar a contestar sus preguntas. Entonces, tomen esto como una oportunidad para aprendizaje, una oportunidad para poner el tema que ustedes estén tratando o el desafío que tengan para ver si es algo que nosotros le podamos contestar. Y aprovechen esta sesión. Leco hace estos tipos de expos y conferencias a nivel mundial. Estamos tratando de enfocarnos un poco más en México. La colaboración de la UNAM y otros institutos académicos nos van a ayudar a realizar esto, pero el agradecimiento de fábrica de la empresa a ustedes por su participación y a la UNAM por organizar esto es apenas el comienzo de lo que esperamos sea futuros eventos. Muchas gracias.
Muchísimas gracias, licenciado Jorge. Pues para dar inauguración oficial a este evento, vamos a pedirle al doctor Carlos Amador que pase al frente y que declare inaugurado este evento.
Con mucho gusto. Muchísimas gracias. Con mucho gusto, siendo las 9:40 del 21 de octubre de 2024, declaro formalmente inaugurado el evento Leco y UNAM para la presentación del análisis bidimensional de cromatografía acoplada, espectrofotometría de masas por tiempo de vuelo para identificación de muestras complejas. Que tengan mucho éxito.
Invitamos al Presidium a que pase a tomar su asiento y pues en lo que hacemos los últimos movimientos vamos a dar la bienvenida al estrado al doctor Philip Marriott. El doctor Philip Marriott es profesor de la Escuela de Química de la Facultad de Ciencias en la Universidad de Monash. Sus principales actividades de investigación se centran en la química analítica, en concreto, la cromatografía de gases, GC multidimensional y GC 2D integral, con espectrometría de masas. El doctor Marriott ha sido reconocido como uno de los 100 líderes e influyentes que han marcado una verdadera diferencia en la última década. Cuenta con 422 publicaciones, incluyendo 393 artículos completos, arbitrados en revistas y actas, y 29 capítulos en libros y enciclopedias. También cuenta con 29 tesis de honor finalizadas, 18 tesis de máster finalizadas, 43 tesis de doctorado finalizados, 22 exámenes de tesis de doctorado por invitación, ya sean tanto nacionales como internacionales, y más de 23,000 citas a sus publicaciones. Tenemos toda una eminencia presente con nosotros, entonces démosle un fuerte aplauso al doctor Philip Marriott.
Just let me move out this presentation. So, let's see. There you go. That's yours. No, that's yours. And this is the one. Close that one. That's not the one. Did I close it? It's this one. That's this one. Okay, awesome. This is yours. Yes. Something that you need? Do you need a massage or something?
I think, yes, we have the microphone. Well, thank you very much for the warm welcome. Thank you, Philippe, for your introduction. I thank also, of course, the UNAM and the Institute of Chemistry for, and Professor Carlos for his warm welcome, and also for allowing us to use this venue. Thank you to Leco for organising the full session we have, and of course to my good friend Professor Omar, who was in my lab many years ago. We published some nice papers, and I'm here to recognise this wonderful history. Today I'm going to talk about, as you see here, going from gas chromatography to comprehensive two-dimensional GC as a way of increasing information content of what we can use for gas chromatography analysis, for volatile separation, and for learning more about these samples. So, I went to Patagonia not long ago, and I saw what is called the Five Brothers. And if you see here, to me, it looks like it's a resolution problem, because we can see five brothers, but not very well resolved. And maybe it's look a little bit like they're isomers of their parents. But sometimes if the peak shape doesn't look too good, we need to know, I'm sure Omar would agree, what the internal standard looks like. And the internal standard, the peak shape is not so good. So if you can't get a good peak shape for your internal standard, you should question your method and see if you can improve your method. Well, I started in cryogenics in gas chromatography many years ago. Cryogenics is a method now used by Leco to implement new methods in comprehensive two-dimensional GC. And just to indicate what my history was in this, I thought that something hot and something cold is a bit contradiction. And so when I was at a conference in Italy, I had an idea about cryogenics and how we can use this for advanced methods. But for me, it is like yin and yang. You might know yin and yang. It's like the opposites. But the opposites together could make a perfect combination. So even though we have a hot gas chromatography oven, if we use something cold, we can do manipulations which are very, very important. And so what I might suggest is, how can we use cryogenics in gas chromatography? If this is a normal gas chromatography system, we can put our cryogenic system just before the detector, which means that compounds that come through the column, you can focus. And then if you implement those or transfer them into the detector, you get a much greater increase in response, which improves your detection. So this is one way we can use cryogenics. Another way we can use cryogenics is to use a cryogenic system to make comprehensive two-dimensional GC with one column and a second column with fast gas chromatography to do some spectacular things. And I will talk about this mainly later on. We can also couple this with something called a Dean switch. A Dean switch just changes the flow. And if it changes the flow, we can direct compounds to one direction or another direction. And this is easy to do now because we have systems that we know how to do this. Another way we can use cryogenics is at the start of the gas chromatography column. That means we can use this to support our injection procedure. Let me show you how this is done. For instance, I can use a cryogenic system to do solid phase microextraction. Can I ask, who knows solid phase microextraction, SPME? Does anyone know? Some people know. It's a wonderful technique invented by Professor Modulation in Canada. This way we can make multiple injections into gas chromatography, and we can compress them or collect them at a cryotrap. And once we do one injection, 2, 3, 4 injections, then we can elute them through the chromatography column. So we can go from a small result to a very large introduction of sample, which means instead of a very tiny peak here, we see a very large peak. or a small peak here becomes a large peak. This improves our mass spectrometry, improves our detectability. Another thing we can do is here. For instance, if we do splitless injection with SPME to increase the amount of material, if we use a cryotrap, then we can get much better result. Look at this. Poor separation, because when we increase the splitless time, we get very poor resolution because we don't focus the compounds. If you use a cryotrap here, you can see this result versus this result. This result is just produced by having a focusing position. Focus the compounds, then elute them through the chromatography column. You see here, I can get perfect resolution here. Here, I get very poor results. And this is very simple to do. And so this is a message that we have ways now of increasing the utility of our method. If we call this the family tree of gas chromatography, we started with packed column GC. We've moved through capillary and down today to multidimensional GC, comprehensive two-dimensional GC. I see this as the future because the information we get is so much better. And I hope I can introduce that to you. This is my tutorial. So this will explain to you how we do this method. First dimension, second dimension column with a modulation system. Now, when I invented my modulation system, it was something that moved back and forward. Leco do something which is a little bit different. I'll talk about this tomorrow, which has the same effect, but it produces it in two different ways. But let's look at the way this works here. We combine this with a non-polar and a polar column, or a polar and a non-polar column, because we want a multi-dimensional separation system that has some, what we call orthogonality. If I look at the compound from the first column, then you see here, if you look at this very carefully, you think, this is not one compound. Because I can see here, maybe the peak is not symmetrical. And if I look at that carefully, I would say, there's something else here, but I don't know what it is. How do I discover what it is? Well, what I do is I slice this peak up into components. And I focus this region here, the next one here, as you can see that. So I focus them up into a very tight band. Then successively, I elute them through the second column. When they go through the second column, I want to separate or resolve each one of these. Let me show you how I do that. I get this result. So this component here is resolved. This one is resolved. And in my mind, I can see I have one component and a second component that were overlapping. But what have I done? I've achieved resolution. So I can see everything in this sample in a way that is really very simple. And I present this as the second dimension separation with the first dimension unresolved peaks. So I get a two-dimensional plot with, I hope, everything resolved. And we'll talk about how we do that later on. So we've resolved something from an unresolved peak. This is what all chromatography people should want to do, get better resolution. This was a system I developed, but as I said, it works the same way as the Leco system. And first column, second column, let's have a look at the criteria. A normal separation column, easy, but a fast separation with a short column. The short column does a lot of work. We have to have a fast detector, which is where Leco come in with their wonderful time of flight systems. Many years ago, we talked with some people. Rick Parry, I don't know if anyone from Leco knows Rick Parry. Yeah? Rick Parry, we had a talk in Utah, in America. We encourage Leco to use their time-of-flight technology for comprehensive two-dimensional GC. And of course, they have done wonderful work with this. So we have to have orthogonal column set, which means non-polar with polar, or polar with non-polar. You just select the columns. It is easy to do. We also have the option of doing target analysis. What does target analysis do? Let me explain. Now, the first column can separate mixtures. But of course, as we saw before, not all compounds are resolved. So if I think there are more compounds here, I can collect that whole band and then put it through the second column. Then I might do this. The second column will resolve this into, 1, 2, 3, 4, 5 compounds. Now here, I didn't know I had 5 compounds. But here, I said, wow, I have 5 compounds. I never knew that. This is discovery. I have discovered something because I now have got resolution. And this is the power of the method. And I'm going to show you, I hope, this. Let me see if this works. Okay. Oh, you can't see that. Let me see. Okay, here we are. Okay, what you see now is modulation, comprehensive two-dimensional GC of individual compounds. So let's just wait a little while. Some of these will be pure compounds with modulated components. And this is me looking at the computer screen. So very soon we'll see one compound, but modulated. There you are. This is one compound. Okay, one, another is all the same compound. And here we'll wait for another one to come through. And again, we'll see it sliced into components. There you go, 1, 2, 3. This is another compound, but it's been modulated, and the modulation gives us a peak shape, or a shape of the modulated components. But you see how fast it is. If a compound is very fast, we compress the compound, its response is very much higher. How many times higher? 20 times higher, maybe. 20 times higher means we can get much better sensitivity. And this is important. Okay, well, I think I can... Let's see if I can find the... I don't see the other. Find my code. There it is. It's very sensitive. Okay, now that we see what we see on the screen, let's go back to what we continue the presentation. Okay, I have a number plate called GCxGC. My number plate, of course, it's not on my bicycle, it's on a car. I will show you. Here is my car. That's my car, GCxGC. I have a number plate on my car, and I drive around GCxGC. And I think people say, oh, GCxGC, what does that mean? If they Google GCxGC, you know what? They find me. My daughter is not allowed to drive my car, because if she's driving my car and she throws rubbish out the window, people say, oh, who is throwing rubbish? GCxGC, Professor Marriott. Oh, Professor Marriott has thrown rubbish out of his car. But why have I got this number plate? I had 4 visitors in my laboratory. 1 professor from Brazil, 1 professor from Portugal, 1 professor from Switzerland, 1 professor from Germany, 4 visitors in my lab. On my birthday, they talked and said, let us buy him a number plate. So my visitors bought me a number plate. Very nice. Let's have a look at some advantages. Well, we have 2 columns. Does it make it harder? No. We understand why we need 2 columns. We have a modulator. Thank goodness, Leco have now got a modulator system, and you can buy this. We have additional separation. Very good. We have narrow cuts from the first column into the second column. And that's the way the modulator works. We have a 2D separation space. We'll see more of this. We have peak compression. So if a 5-second wide band is compressed to 0.2 seconds, that is 25 times increase. Much better. Better sensitivity. Improves mass spec detection. Why? Because you've got pure compounds. You also have more pure mass spectra because you don't have background bleed. So the mass spectrometry quality is much better. The 2D separation is a unique display of the chemistry of the compound, and that's important. We call this disruptive because it's not just one dimension. We have to think about 2 dimensions. And once you do that, it's easy. And I could call this making order from chaos. Well, this is the analysis of coffee. I call that chaos. Why? Because I don't know what each of these compounds is, and they might be overlapping. In fact, all of the compounds overlap. With mass spectrometry, it doesn't really make it that much easier because I have overlapping peaks. But chaos because any compound can elute at any time. Let's have a look at comprehensive 2-dimensional GC of coffee aroma. This is 1 coffee bean in a vial, SPME, GC by GC. And you look at all the compounds here that were here. This is now order, because I can get a mass spectrum on every compound. Look at this. I can get a mass spectrum of that compound, of course of the big compounds, but they're all pure. If I look at this, a peak here has 1, 2, 3, 4, 5, 6, could be 7 compounds overlapping. How does my mass spectrometer with 1-dimensional GC know that I've got 7 compounds? It won't. But here, it's easy. This is something we published a little while ago. 1, 2, 3, 4, 5, 6, 7. We don't have 8 columns in our GC, but we have combinations of columns which we use. For instance, if we go through this with a modulator to a second column into a detector, that is comprehensive 2-dimensional GC. That's the way we view this. If we have another system, such as this, we can do pressure tuning through the modulator, through the second column, to the detector. We call that pressure tuning, GC by GC, mass spec. Pressure tuning is a very nice method that we developed for comprehensive 2-dimensional GC. I will talk about this tomorrow in my workshop. We can also do GC modulator, third separation into a detector. This is GC by GC by GC. Some professors have worked on this, particularly Professor Sinovac the University of Washington. It's a bit more complex, but for him, it resolves things for petroleum much better. We also have a method, which, okay, maybe I should go back, where we have one column, a second column, and a third and a fourth column. This is for a very special technique where we look at compounds that do interconversion. And I will talk about this at the end of today, if I have time. Okay, now we can also have an accurate prediction of the first dimension retention. Because if we modulate peaks like 1, 2, 3, 4, 5, this is the biggest peak. Is that the retention of the compound? Because if we've modulated the peak, it depends on how I modulate as to how I predict the retention of this compound. Is it important to know retention? I think so. Because for many, many years, people say, I need to know the retention of a compound in my GC. Because it's comprehensive two-dimensional GC, I still need to know the retention. And so I would like to know the peak maximum here. Now, this peak and this peak maximum might be different. So let me show you what I can do here. I can fit this shape to the modulated peak, and you see I have a difference in this and that. So there's a slight difference in retention time of the first column peak and the modulated peak. So we can fit this together to get an accurate first dimension retention. We did this some time ago, but that's also useful. Do we expect 0% retention RSD? I don't think so, but sometimes, you know, if you do multiple injections and you get the same retention time for that modulated peak, you'll get 0% RSD. And people will think that's not right, because there was always some uncertainty in my retention. So if the first dimension peak has a slight retention uncertainty, why doesn't this have retention uncertainty? It's because the modulator makes it exactly the same all the time. And so we looked at something here, which we called GC by GC with mass spec super resolved separation. That's what it is, super resolution. And what we can do is look at a contour plot and have centroid peaks which show the accurate retention time of all the components, first dimension and second dimension, to give us greater certainty. And I'll show you what I mean by that very soon. So let's have a look at these symmetric peaks here. This means we modulate fast. This one means we modulate slower. So here we have 3-second modulation, here 7-second modulation. But note that I have a retention of about 26 minutes. I had to do this in order to do the experiment. And I wanted to change the modulated peak, the number of peaks, in order to do this experiment. And I came up with a metric called modulation ratio. Now, modulation ratio, if it's about 7, means we have 1, 2, 3, 4, about 7 big peaks. Modulation ratio of about 3 means we've got about 3 good peaks, about 3 good peaks. But again, look what I can do here. I can look at that and I can overlay the profile. If I do the next one, I can overlay that as well. So I don't lose information. I can fit the first dimension peak on the modulated peaks, which means it is a true chromatography process. I haven't lost anything, but I've gained sensitivity, separation power. So orthogonality, what is orthogonality? Does it matter? How do we get it? Can we prove if it's useful? Let me give you some answers. What is it? Provide unique identification of peaks by using extra orthogonality. Does it matter? Yes, because if we get more orthogonality between two dimensions, we can get better separation. How do we get it? We change the phases. The first column and second column, different phases. Easy. Every chromatographer will have different polarity columns in their drawer to use as necessary. So this is the Brazil orthogonality experiment. I have many collaborations in Brazil. In the south of Brazil, there is a special beer. Maybe, Tiago, you know what the beer is. It's called Polar. Let me show you. Polar in Porto Alegre. If you have a polar beer, do you have a non-polar beer? I don't know. So let us see. First of all, Skol and Polar. Well, Skol is not polar, so it must be non-polar and polar beer. Okay. Or I can make a polar beer with a non-polar beer because I wrote non-polar on the beer. And in fact, one of my friends then gave me her lipstick. So I wrote non-polar. You will see. Here it is. See the non? That's the lipstick from one of my friends. And it's orthogonal because it's at right angles. We have non-polar and polar, just as in columns. We have a polar and a non-polar phase to give us what we want. We did an experiment some years ago where I mixed a number of different phases, non-polar and polar columns. Now you see this is the first dimension. I said I want the first dimension to be comprised of a non-polar column or non-polar with a small amount of polar, non-polar with the same length of polar. So I'm changing the length of the first column. Let me show you how I did this. The first dimension was 2 columns. The second dimension, I didn't change, except in the next experiment. Now, what does this do? If you change the percentage of the non-polar and the polar column, all I do is change the elution temperature of the compounds. So if I change the percentage of columns, I change the elution temperature of different compounds. That's all the columns know. All the compounds know is what temperature do they get to the second column. And I will show you this here. This is column A with a polar second column. I'll keep the polar second column the same, and I'm going to change column A. Let's have a look at this. I'm going to see I'm changing the first column and see how the chromatogram changes. Now what's happened? I have 20 meters of polar column and a polar column in the second dimension. I have got no orthogonality. Because I've got no orthogonality, the compounds don't change in the 2 dimensions. Let me go back. See, I'm adding more of the non-polar column. And see that? So I can change the whole chromatogram in very interesting ways just by doing that. Now, let's go back. Okay. It collapses into a correlated chromatogram. Now, I'm going to change it to a non-polar second column, and I've got a non-polar first column. What does it mean? I get correlation. I've got no separation. I'm now going to change the first column with a little bit more polar nature. And here's the result. See how I start to get separation of those compounds? And look at this, I get amazing separation here. And these ones are alkanes because I've got a non-polar second column. So alkanes elute latest on the non-polar second column. And all I'm doing is changing the first column nature. Well, I love this experiment because it tells me what orthogonality really is. Okay, we also did some fatty acid analysis on this very polar column. It's an ionic liquid column. It's the most polar column that we have. So if I combine a very polar first dimension column, these are now second dimension columns. This column is also very polar. Reduced polarity as we go down here for the second dimension. These are all ionic liquid columns. Now have a look at this. IL-111 with IL-100, IL-111, it's very similar polarity. So we don't have much orthogonality. As we reduce the polarity of the first column, the second column, we start to get separation. You look at this and you say, wow, this is like a beautiful GC by GC result. And this now is looking at some also reduced polarity compounds until we have a very non-polar column. A non-polar column with a very polar first dimension column, we get this result. And what it means is you've got too much orthogonality. The columns are too different. Now, if you look at this and this, sorry, where it is, sorry. If you look at this and this result and this result looks very similar. So if I combine a first dimension 111 with a 76 second dimension or a BPX 70 second dimension, this and this look similar. But as I go to lower and lower polarity, I get far too much separation on the second dimension because the columns are too different. And hopefully that was maybe familiar to you now. So these are too different. So I have to tune my GC by GC separation in a way to make it good separation performance in the two dimensions. But we are the only ones who do this with this sort of column. This is just to demonstrate what we think about orthogonality. This one now shows a second dimension, again, of the BPX5 column. The retention of some of these compounds on the second dimension is about 25 seconds or 20 seconds on a 1 meter column. And the second dimension performance is absolutely spectacular. I think we have about 18,000 plates for the 1 meter column. This is almost like a record, I think, because the performance is incredibly good, but we can't have retention, which is too late, because I want all the peaks to be resolved within my modulation period, maybe 4 seconds or 5 seconds. If we retain compounds 24 seconds, we have too much retention on a 1 meter column. Okay. Another visitor I had is Glaucima Resenge. He was from Brazil, from Minas Gerais, Belo Horizonte, if you know Brazil. We published a paper about GC by GC technology for non-targeted analysis. Because if you have non-targeted analysis, and I think some people here I was talking to about metabolomics. non-targeted metabolomics or analysis is what you need. And so this is where it's very good. And we think that GC by GC offers us coverage of all the compounds because we can see all the compounds in the 2 dimensions. And once we have that knowledge, we can work out the importance of certain metabolites and things like this. So we published something else with one of my students who is now a professor in Malaysia. Challenges for analysis in flavour and fragrance. We do a lot of flavour, fragrance analysis, talking about why you need comprehensive 2-dimensional GC. Recently with another student who is Yada Nolvachai. She's from Thailand. I get visitors from students from everywhere. We published something called Separation Multidimensional. Is it worth the effort? Because multidimensional, you have to make the effort to understand and also get the technology. Of course, we say, yes, it is worth the effort because we know. Both of these were in Journal of Agriculture and Food Chemistry. Is it worth the effort? Well, let's think of the effort. We have a new technology. We need to learn. Okay, so that's a challenge. We need to look at standard methods. Maybe there are not many standard methods. You have to go to literature and find out what you need. Maybe we deal with unfamiliar ways of expressing the compound or the result. If I look at fatty acid methyl esters in 1 dimension, I recognise it. I know what it looks like. In comprehensive 2-dimensional GC, I have to learn what it looks like. We have lots and lots of compounds. Is that good or bad? I think it's good, because if we know more compounds and we can identify more compounds, we know our sample. We have good multidimensional GC history, so we should be able to do this. Okay, new technology, we have to do more training. Is that bad? We have to expend effort. We have to learn. Lack of literature, standard methods, is that bad? Well, no, because we go to literature, we learn. Every time we read the literature, we understand more about what we're doing. We're dealing with unfamiliar display of composition. We have to learn. If you want to learn, you learn. You can make all of these into happy faces by learning. Sheer number of compounds, bad? No, it's good. If someone said, I've got a sample analysis in 1 dimension, but I don't have resolution, are you happy or are you sad? You should be sad, because if you can't resolve compounds, how do you know if they're important? You should be happy to get more separation. We know good GC history, it should be good. We know our samples better. Oh, happy. Because if we know our sample, we can say, yes, we know exactly what's in that sample. We should be happy. Instead of closing our eyes, we open our eyes. Compound identification. Look, I won't... It's sort of what we've already talked about. We have less matrix interference. We have better mass spectrometry. We have, importantly, first dimension and second dimension retention, peaks in a certain place, which gives us information. So, with Yada from Thailand, we had a final comment. Look at this. If you are not using GC by GC, you will never know what you are missing. Because you'll always see, I see 1 peak. Is that 1, or is it 2, or is it 3? I don't know. If you don't know, you'll never know what you were missing. Comprehensive 2-dimensional GC, you know. So GC by GC has selection, separations, sensitivity improvement, etc. Let's have a look at this. This is comprehensive 2-dimensional GC. This is 1-dimensional GC. but the one-dimensional GC was 2.5 times more injection. So these peaks in comprehensive would be up here. So this little peak here is very tiny, but here, multiply it by 2.5 times, wonderful response, and better mass spectrometry. So we get better sensitivity. And look at this, we've got a couple of peaks here, and this looks like one peak, that one looks like one peak. What about separation? Well, let's have a look. First of all, let's have a look at this. One-dimensional GC time of flight, there it is. That's the baseline. And you might say, there's no compound there. If you modulate, you get this result. And you say, wow, I see a compound. Here, I don't know what it is. But here, I can see a wonderfully modulated compound. With mass spectrometry, I get identification. So sensitivity does improve. And better separation. Before, for this peak, I showed you that just now, I can see one peak, I can see another peak. So I've got two components there. Most people would look at that and say, one peak, identification, that's my result. And I'd say, you are wrong. You are wrong, because there are two peaks there, two compounds. You say, oh, I never knew that. Yeah, you were right. I am wrong because I didn't do this technique that allows me to see extra information. Okay, this is aspirational, because we would say once we identify a peak, we hope that the position is always the same for the next and the next and the next analysis. Let me show you. This is Blanca, Barnea, Corantini. These are volatile compounds from olive oil. And this is one-dimensional GC, okay? We can maybe see patterns, and maybe this compound might be the same as that one. We have some overlaps, well, 3 and 4 are very close together. What's the comprehensive two-dimensional GC look like? Here it is. Now, you look at this. I've got much better separation, and I can see a peak here and a peak there. I see lots of components there. But let's have a look at this. See, my internal standard there and there and there is always at the same position in 2 dimensions. And once I see that retention of the internal standard, and I see it's the same retention, of course I'm happy. And this is what I expect, because everything else has the same retention precision. You look at this, see those 5 peaks there? 5 peaks there? Well, I see 3 peaks there, but those 2 peaks, and the peak there, the same position, I bet they're the same compound. They must be the same compound. So once I identify one of the compounds, I know it in all the samples. You see this? I've got some components there, some components there. Same retention position, same compound. That's powerful. Because once you identify them here, you don't identify them in all the rest. You use retention. That's it. Wonderful. You can't do that with 1 dimension. Let's have a look at some coffee. See these? There's 4 peaks there, maybe 4 peaks there. Those peaks are the same compound. There it is. That compound must be that compound. How couldn't it be? It's in coffee. It must be the same compound. Once you identify it, you say, oh, same retention, same compound. And you can see also here, that peak must be that peak. And we can also look here. That cluster and that cluster has some pattern. And the pattern tells us if they're the same compound, same retention, same identification. Illicit drugs profiling. This is Marion Jones. I can tell you who she is. She was at the Sydney Olympics. She won. Oh, she's very fast. Look at this. She won 5 medals. If she goes back to America, she will make $10 million every year because she's an athlete who won all these gold medals. Then she became sad because she was found to have doped with a particular dope. It was called the clear. The designer steroid called the clear. Undetectable by the techniques that were used in those days. There's a wonderful story about this. She was never caught, never tested positive, but they found her name on a computer file from a company that provided steroids. And because of that, she lost her medals. Why not? Well, the solution is we need full scan methods. We need to archive material. In future, if we find in GC by GC, if we find a peak at the same position, we don't know what it is. In future, we might say, that peak, we now know what it is. We look through the historical record, guilty. We found drug problems. So we can use comprehensive two-dimensional GC with mass spectrometry to archive material and discover. This is ecstasy profiling. Non-polar, polar column. Look at this. We profiled ecstasy. We got some samples of ecstasy. I had a student from Macedonia who was from the police laboratory in Macedonia, forensic scientist, and he did a study on this. Now, all we need to do here is profile the compounds. Look at this wonderful separation. And this is what we found. We found all these compounds here, which all of a sudden matched mass spectra of safrole, isosafrole, MDMA, all these sorts of things. So all of a sudden you can see that you've got a record of all the compounds in this ecstasy capture. And so here we can see safrole, a peak 14, we had peak 16, we had peak 27, we had then the final ecstasy. So we can see the production process of the ecstasy manufacture through the profile of the fingerprint of the final product. And we might be able to relate that to a particular laboratory, because the laboratory who makes lots and lots of material, sell it, will have the same profile if it's the same batch. And so then you could know if captured ecstasy has the same background or the same source. And we did this also for heroin and also for cocaine profiling. Okay, this is quite different to these two. And you could probably see that by one-dimensional GC. But there's additional information which probably is used for intelligence, for police, for forensic scientists. We've also done some components which are at low concentrations, which are chemical weapon components. So here we have tabon, sarin, and soman, and we detected these at low concentration. We also do comprehensive two-dimensional GC. Tomorrow, I'll talk a little bit more about this and about what techniques we can use for things like pesticides, organophosphate materials, and also chemical weapons, and why certain detectors have certain advantages. So that's tomorrow. So unresolved complex material is something from petroleums. This is a classic result of unresolved complex mixtures in petroleum analysis. And you look at this, and the only way of getting information here at the moment is doing some mass spectrometry. If I looked at the mass spectrum of this peak, what's under here? There could be 10 or 20 compounds under there. How do I know I get the right identification from mass spectrometry? Well, comprehensive two-dimensional GC, this is the result. So how does this compare with this? Petroleum people must love comprehensive two-dimensional GC, because I can see here at any particular point I have aromatics, I have olefins, I have cyclic compounds, I have alkanes. At one point I might have 15 different compounds. My mass spectrum will not tell me that on one dimension, but here it will tell me. So I can change this to, this I know now is a non-polar column and a polar column, because these compounds are naphthalines. I recognise them. If I change this to polar, non-polar, I flip the response in the second dimension. So these ones are now alkanes. Let's go back. These ones are alkanes down here. These are cyclic compounds there. Next case, these are alkanes. These are cyclic compounds. These are the aromatics at the bottom, because it's a polar, non-polar arrangement. And the information content is incredible here. But it's not being information and being scared, it's information and doing something, because you've got something to work with. And so here you can see biomarkers and things like this. We've got monoaromatics, diaromatics, other components. Everything there is easily identified. And I know that, for instance, Petrobras, I often go to Rio de Janeiro. Petrobras has at least 4 GC by GCs, and they do this sort of profiling all the time. Shell, ExxonMobil do this. Now, I don't have a lot of time left, so instead of this part, I'm going to jump forward to biofuel. Okay. Now, biofuel is something that our Air Force is interested in, because new biofuels are the fuel of the future. And in these cases, the biofuel tends to finish about C18. My student was concerned, she was from the defence industry, and she was concerned about, if you keep biofuels for a long time, you get oxidation. And she wanted to know, what are the oxidation products of the biofuel here? So she tried, for years, she tried many methods before she came to my laboratory. She said, I still cannot get the polar compounds identified. Solid phase extraction, liquid extraction, all sorts of things she tried. She brought the sample to us. We did a workshop. I said, bring some samples. She brought this sample to us. We did comprehensive two-dimensional GC, and we showed that. We said, one analysis. I said, these are your saturated compounds. These are the polar oxidation products. Alcohols, ketones, acids. She looked at that, and she looked at her watch and she said, it's taken you 1 hour to get this result. I've worked for 2 years and I couldn't get this result. For 2 years, I showed it in 1 hour. So she became my student. And because she said, I have to do a PhD because this is too important to us. And so she then did, look at this. I mean, acids, aldehydes, ketones, alcohols, it's all there. Why is it important? Because with some of these fuels, if you get oxidation, you get particles formed. The particulate polymers block the fuel intake for the airplanes. You can stall the engine if you don't have purity. Okay, so To cut this story short, we did multi-dimensional sampling strategies as well, where we take a component here, we have 12 seconds component sampling into into multi-dimensional GC. So we sample, analyze, but we made another injection. We shifted the window by 12 seconds. Next injection, shifted it again. And we did fast analysis on the second dimension. Okay, 12-second heart cut. This one was eluted in 2 minutes. And then we did the next sample, analysed for 2 minutes. And you can see here, polar compounds, non-polar compounds. We don't worry about the non-polar compounds. We want the polars, because they're the problem compounds. Because that's why you do antioxidants in some of these fuels. But we can do another technique. Here's the other technique. We can collect that. We can cool the oven. We can then do a very slow analysis on the second column, and we get this result. Look at this separation here. This is a beautiful this is quick separation. This one is a long separation to discover what compounds might be there. We can then go back to comprehensive two-dimensional GC, do it all in 1 hour, or we can do slow analysis, learn, study the compounds, then make a decision. So this is great for discovery. Let's have a look at this. Okay. Some people called Gordon did a study years ago on tobacco, essential oils. They did multidimensional GC. They did 48 hours of analysis to do multidimensional GC, tobacco, essential oil. We did peppermint oil. We collected this compound here, or regions here, 3 compounds. We collected it, cryotrapped, analysed it on the second compound. We got this result. So from this, we get that in about 20 seconds. So all those compounds here were in there, not resolved. And we can do this within about 30 minutes. Gordon took 48 hours. We can do that in 30 minutes. And I think, well, I have to go to the oxime. This is the, I can talk about olfactometry, which is another wonderful technique, but I'm going to go to the oximes, and this is where I finish, so please, a few minutes more. This is looking at molecular geometry changes in GC by GC. This is some of our most recent work, and I get excited, so please bear with me. I'm just so excited. This is peak bridges due to in-column transformation. Now, this is some years ago. This is 2015. I reviewed this paper, and I thought it was so nice. I said, yes, accept, because it's too important. Because we know some of the analysis problems of this area. We've done this when I used to live in Singapore, 20 years ago. This is myrrh oil. Do you know myrrh? Myrrh. It's a fragrance, myrrh. Now, this is a one-dimensional GC analysis, and you might say, wonderful, wonderful analysis. But have a look at the baseline. Do you see something in the baseline? Most people don't, but I'm going to reveal. Watch this now. I reveal this. See this? C, D, and E. These are transformation. Some compounds change structure during GC. And this is what it is. See this and see that? These bands, myrrh oil, these are the processes that happen. Germacreme changes to alanine in the gas chromatography. Can you see here, if I go back, can you see here the process? No. Well, maybe you can see something there, but what about this? Can you see the process here? It's like you can see everything. It's so beautiful. And we have done this, and you can see here, the same processes, here, expansion. But there's a different process. See this tail? It goes to, it sort of finishes. This one gets to here and stops. So we interpret that as being two different processes, two different kinetic processes. You can't do this any other way than comprehensive two-dimensional GC. And so just this week, I've got a third-year student who's doing this project. She's giving a presentation tomorrow, and she's learning this process and this process. What happens is this compound gives rise to this compound here on the column. And she's looking at that and trying to understand how the interpretation is. This is temperature programming. This is isothermal. Isothermal means that the compound, the column stays at the same temperature. Therefore, this tail is the same position. You can see again, see that this compound gives rise to this tail, ends in this compound here, and so that now is something that we can interpret. We've done this with oxenes when I was in Singapore many years ago. Relevance to someone at Cornell University, might cover that. Comprehensive two-dimensional GC. Compound B converts into compound A, showing this tail. Compound A converts into compound B, shows this tail. In GC by GC, you can see this. You cannot see it in one dimension, because in one dimension, this plateau, you don't know how much of compound A and B are there, but we can see it now in two dimensions. And we've done many processes, I won't talk about this. Look at the complexity here. This is the result. We can interpret this by understanding how this, this process happens. We've also done it with pyrethrins. This compound, which is pyrethrin, converts into isopyrethrin by the bonds shifting shape on the column. And here it is. You can see this band and this band in the one-dimensional GC. And you can see it in comprehensive two-dimensional GC here. There it is, that band and this band. And it's easy to see and easy to interpret. Well, that's the end. I'm 2 minutes over. I went to New Zealand. On the beach was a black beach, black sand. My wife was walking up the beach, and I looked at this and said, oh, I can put GC by GC, and I put MDG. I could take the photograph, as you see there. My wife came back after walking and she said, what are you doing? She said, look what I've done. I've made GC and multidimensional GC. She said, we're on holiday. Why are you still thinking about work when we should be on holiday? She said, if you put the names of your grandchildren is better than putting work. Anyway, that was in New Zealand, and I was still thinking about work. I've had many students from many places around the world, many visitors, including Mexico. Omar, there was my visit from Mexico. And they've all enriched us by bringing complex problems and solving them. So thank you very much, and tomorrow I look forward to talking about more workshop information. So thank you for your attention.
Thank you. Thank you so much, Dr. Philip. Thank you for your great lecture. As we were told, if you have any question, please give it to the staff ladies so we can start. But in the meantime, we have a couple of questions. The first one, how about your tie? That's a great tie. No, just kidding. The first question. Sorry.
I can answer if you like.
Sorry, that was a real question.
A birthday present.
First question. What are the primary applications in industries and benefits from GCxGC analysis, and what type of samples are typically analyzed?
As we get more experience, almost every area of GC analysis can be done by comprehensive two-dimensional GC. Even simple things that you might think on pesticides, with maybe 3 or 4 pesticides. There's many times if you've got a sample analysis of a simple mixture, sometimes peaks overlap. And if they overlap, your analysis becomes compromised. So even in those areas, yes. So environmental, very important. Essential oils, perfume. I work with a perfume company, or worked with, and they have to use comprehensive two-dimensional GC to identify perfumes, essential oil mixtures and things like this. I think I showed you some data on complex petroleums. Complex petroleums, its perfect technique is comprehensive two-dimensional GC. So Petrobras, as I said, Shell, ExxonMobil, all of the petroleum companies use comprehensive two-dimensional GC. Not for everything, because if they can work out what they understand from comprehensive two-dimensional GC, they can go back to say, okay, you can do one-dimensional GCMS, because we now have information to help you even on your one-dimensional GCMS, because we know what's in the samples. But more often they do this. And Unilever in food analysis, I have a very good friend who works in the Netherlands, Unilever, for food analysis. Every sample that comes from a new process, they do comprehensive two-dimensional GC, because they want to look at the process, they want to see everything, and then using that information, they said, this sample we can analyse by one-dimensional GC, FID. This sample, needs GCMS. This sample we always have to use comprehensive two-dimensional GC. So they look at the sample, look at the composition, and then decide how they do the analysis in future. But they use screening GC by GC as their first step to get information and then make a decision.
Thank you so much. Another question, and this goes on the other way around. What are the limitations and challenges associated with GCxGC?
So the first part was the...
What are the limitations and challenges associated with GCxGC?
Okay. Identification, the limitations. Limitations and challenges often is related to how much experience you have. And at the moment, we don't have many students who have come up learning comprehensive two-dimensional GC. So some companies might be limited in who can they get to use comprehensive two-dimensional GC, because not many students know what to do. So if you don't have the training, you don't know how to implement the methods. And so we need more people to learn the techniques, to use the techniques, to understand the techniques, and then put them into industry who have the techniques of comprehensive two-dimensional GC. It's a bit of a balance. You have to have the students, you also have to have the instruments. And if you get the balance right, then we go forward. But limitations is, and I indicated that there's learning, there's ongoing training, quantification, getting used to looking at the chromatogram. As I said, if I do a fatty acid analysis, I can see, okay, C12s, C14, C16, C18, I get to recognise it because I've done one-dimensional GC. Comprehensive two-dimensional GC, if I give that to someone who's done fatty acid, they say, I don't understand it. But the more they do, then they say, I can see, I understand everything because I'm familiar. So the challenge is to get to recognise the result. But also, to see if there are standard methods available. In the petroleum industry now, there are some efforts to have standard methods using comprehensive two-dimensional GC. There are some methods which are now assigned to comprehensive two-dimensional GC. They say, here's the method, anyone can use it. But it's also like a standard method for anything. Once you've got the standard method, you follow the method, you should get the result. We need more methods, comprehensive two-dimensional GC, so that people can look at the method, apply the method, get the result they want. So it's training, it's methods, and it's learning.
Awesome. Thank you so much. If there's any other question, please let us know. Or if you wanna have the microphone, we can share it. So another question that we have here. Thank you. Okay, I will check the questions, but another one, and maybe it says, how does GC times GC compare to other multidimensional chromatography techniques, such as LC times LC?
GC by GC is far easier than LC by LC. The reason for this is because we have a gas which gives us speed. We can make the columns short and fast. Of course, you can do that with LC as well. But in LC by LC, you have to collect fractions from the first column, then re-inject the fractions into the second column. Very hard to do online, but you can do it that way. You then have to work out how your different chemistries. Do you want to use, well, normal phase with reverse phase is very difficult. Maybe Hillic with reverse phase might be something easier, but you still got to have that fraction, and sometimes it takes you a long time. It extends the method out. We can do GC by GC in the same time as one GC analysis. No longer. So if you have a 30-minute one-dimensional, we can make it 30 minutes multidimensional. We have done some samples of allergens in GC by GC, 5 minutes, because we had temperature program ramps of 20 degrees a minute with very short columns. We're the first people to do this. So we can make it very fast. You can't do the same thing in LC, because LC has the limit of the solvent.
My goodness, a great bunch of questions. Let me try to
the next question is,
summarize.
Where's the tie from? No,
that's at the end. Which is the minimum concentration of one analyte to be detected or identified?
Well, that's interesting, because tomorrow I will show some detection of histidine, amino acid histidine, by comprehensive two-dimensional GC with very, very low concentration levels. Look, it really, if you know GCMS and you've got a certain level of detection with comprehensive two-dimensional GCMS, you should be able to get 10 times improved limit of detection, 10 times lower. Of course, if you have a quadrupole versus a time of flight, that's a difference as well. There's many uncertainties there, and if you have high resolution, it's different to normal resolution. But generally, I would say 10 times improved. But you get 10 times improvement, but you get lots more compounds. Everything is, that's why we have happy face. We're happy about that.
Awesome. There are some questions that I know that you will lecture tomorrow, but there's a very interesting one. You have a fan. How can I become your student? What do I need?
Funding is a question. Well, that's usually, well, have to talk first. We'll talk. But I do get excited by giving presentations.
Awesome. Because of the lack of time, I think we're done for today. I know that tomorrow you will continue with the GC and GC lecture.
Workshop,
so
yes.
There are a lot of questions that will be covered tomorrow. Don't worry about that. Please be tomorrow here. And I think that that's it. We can give a big applause to Dr. Philip Marriott. Thank you for this.
Thank you very much.
Ahora, cambio un poco español. Vamos a tener un receso de 15 minutos. En la parte de afuera hay coffee break, si quieren tomarlo. En 15 minutos iniciamos nuestra sesión. Sigue el doctor Alan Griffiths. Y en caso de que, por favor, si van a salir y van a estar caminando por áreas húmedas, dejen los receptores para que no haya ninguna complicación. Se pueden estar cargando. Y en caso de que estén en esta zona, sin ningún problema. Se les entregaron unos presentes al inicio, esos los pueden utilizar también para tomar ya sea el café o el agua, para seguir bajo el ambiente medioambiental. Muchísimas gracias, nos vemos en 15 minutos.
No, estos son...
Dime. Ajá. Ok. Se cubrió con sí, ahora sí que no. Hacemos una prueba de señal ahorita, voy a subir, perfecto. Y los dos guardo. Seguro, muchas gracias. With this one, you move forward. Okay. This one is back. And if you want to pointing. And if you want to black the screen, you click this one. And it should be black. But it's still active. You just click it.
Cool. Do you want me to sit down there during your introduction, or stand up here? Okay.
nuestro programa. Muchas gracias. Muchas gracias por su atención. Vamos a continuar con nuestro programa. La segunda plática del día de hoy es a cargo del doctor Alan Griffiths. Él es el director global de la rama de Ciencias de la Separación en Leco. Él está basado en Londres, bueno, en Manchester, Inglaterra, Reino Unido. Y él es experto en Ciencias de la Separación. Ha trabajado extensamente con tecnologías avanzadas de cromatografía y espectrometría de masas en Leco, con una carrera diversa que abarca desde la construcción de espectrómetros hasta la capacitación a clientes y la presentación de conferencias sobre GCMS, GC por GCMS a nivel internacional. El Dr. Griffiths combina conocimientos técnicos profundos con una habilidad para comunicar la innovación y precisión de los instrumentos de Leco. Démosle un caluroso aplauso y seguimos con esta segunda sesión.
Thank you. Something unique? Thank you. Thank you for being here. I really appreciate it. Thank you for inviting me. I didn't quite catch all of the language. My apologies for not speaking Spanish. But I heard the word expert in there, and I'd just like to say I'm nowhere near the expert of Professor Marriott, and no, you won't be a good, I wouldn't be a good professor if you wanted to be my student, so bear with me. I work for Leco. I've worked for Leco for almost 20 years, working my way through as an engineer and working my way through to sales into the position I am now. So today, I just want to give a little bit of an introduction to Leco as a company, where we come from and where we fit into GCxGC. This is just a really nice picture I like, so I stick it on the front. There's my introduction. I'm the Director of Global Separation Science Sales for Leco, and I'll go through a brief history. Leco Corporation was the laboratory equipment company founded in 1936 by Carl Schultz. And this is where the name Leco comes from. Leco, the laboratory equipment company. We introduced the carbon analyzer, rapid carbon analyzer, for the steel industry back in 1936. It took a process which was about 24 hours long and brought it down to about 20 minutes, which was a massive step forward in analysis, in just the concept of analysis and of automation. World War II came along. The carbon in steel, if you're not aware, is what helps it with its structure and its strength. So being able to understand how much carbon is inside steel is very important to know whether your tanks are going to fall apart, whether your bombs are going to blow up, all of these kind of things. It became very important in World War II. It made some differences to Leco. After World War II, there was the sulfur determinator and many more pioneering innovations since then. In the 1970s, President Nixon brought in the E for Export Awards to try and encourage American companies to travel around the world and export their goods. And Leco was one of the receivers of that award. And the gentleman you see there is Robert Warren. And he received that award off President Nixon. And he became, later on, he became the CEO of Leco Corporation and the president of Leco Corp. In the 1980s, the age of the computer came along us, along with some somewhat interesting logos. And this made a huge difference to what Leco was doing. So we had the computers, self-calibration, microprocess, etc. More innovations and more steps forward. So I'm going to step away now from Leco and go into GC TOFMS. Quite often within the world of science, we find that specific areas become quite important to technologies and into understanding, into learning and innovations, etc. South of Manchester, an area called Cheshire is a very good example. Arguably the first mass spectrometer was built there by Philips, and now companies that are there include Waters, the Leco HQ is in that area, Agilent has one there, Isotopex, External, there's loads of them, all in that area. And the state of Michigan in America is really important to GCMS, specifically GC-TOF-MS. In Midland, in Michigan, the first GCMS was built in the Dow Labs in 1957. The two gentlemen you see there are Fred McLafferty and Roland Golk. These are kind of the godfathers, really, of GC-TOF-MS. They were playing with a TOF. You can see their TOF there in the olden days. TOFs used to be these long tubes, typically 1 meter long, but theirs looks a bit longer than 1 meter. And they had this bright idea. They'd heard of this thing called a gas chromatogram. And they had a friend in Detroit who had one. So they drove down there in their car, grabbed it, took it up, put the two together, and invented GCMS. The first GCMS was in fact a GC-TOF-MS. Then in Michigan State University, which is in East Lansing in Michigan, a group of people got together with the idea of creating fast GC-TOF-MS. One of the problems with GC-TOF-MS is the amount of data it creates. TOF-MS is phenomenal. It looks at all of the masses all of the time, and you get lots and lots and lots of data. And back in the 1950s, they simply could not cope with the amount of data that it produced. Then the single quadrupole was invented, and that's basically a mass filter. And that made GCMS much more capable of being used within laboratories and research institutes, etc., because it was simpler. And in Michigan State, they had an idea that now we had fast computers, maybe we could make a fast GC-TOF-MS. And so a group of people got together. They were struggling a little bit with some of their electronics. So they enlisted a freshman, Kevin McNitt, who was a computer scientist, to work on the systems with them. He became very good friends with the ion optics expert, Artyev Vyacheslav, otherwise known as Slava. A bit easier to say his name. He's from Moscow State University, but moved out there. And between the whole group, they built the fast chromatographic detector, the FCD. This is Slava and Kevin, and this is at PitCon in 1995. There was a really important development that Kevin McNitt made, which was the integrated transient recorder. And that gave them the ability to analyze mass spectra at an extremely fast rate, way faster than a computer could deal with at the time. So he made this system so that it could take that information and transfer it in such a way so that it could be recorded on a hard drive. This was a huge step forward. It was at PitCon that Leco met these two gentlemen, and Leco decided to bring them on board. Leco is based in St. Joseph's in Michigan. So here's Lansing, and just to East Lansing is where Michigan State is. So you can see all the important parts of GC-TOF-MS all came from the very same state. This is St. Joseph's, where Leco are based, at the various facilities. You can see this is one of the manufacturing facilities. Down here is the service area. Over here is another part of the manufacturing and the warehouses. We've got some research and development here and here. This thing here is a big block, which is for testing electromagnetic radiation. It's got some lovely windows on it that are completely fake. It's just a concrete block because they couldn't have windows, but the neighbors and the people in the area didn't like the fact there was this building without windows, so they have fake windows on it. Just behind this box is the place that I normally work when I'm in America, the Customer Experience Center. You can see it's quite an important area of St. Joseph's. There's not a lot much going on at St. Joseph's. This is Lake Michigan, and up there somewhere, just around the corner, is the small town of St. Joseph's. So the innovation of the fast GCMS based on time-of-flight technology in 1995, and that's the photo from it. It's an important photo. 1 year later, Leco brought out the first commercial GC TOF-MS, the Pegasus. And then in the next decade, a move to modulation technology, which we've been talking about today, sees Leco become industrial leaders in comprehensive two-dimensional gas chromatography. In 2011, we brought out the high-resolution TOF-MS, the HRT, for accurate mass analysis. At the time, I was asked to do a publication to write for an article for Chemistry World for the Royal Society of Chemistry in the UK. And so I asked Slava and Kevin if they could remake this photograph, but with the HRT, which they kindly did. However, it was later on I was talking to Kevin and Slava, because they also did one for the BT as well. And I noted, I don't know whether you can see from there, but I noted that Slava has exactly the same tie in all of them. And I commented that he's such a successful scientist and a man that how come he's only got one tie? To which he commented, oh, I knew you were trying to copy this photo, so I got the same tie. To which Kevin was extremely upset because he'd not told him and he wore a different tie. But still, as a result of all of this, we became best in class of the full mass range, fast data acquisition, became the kind of hallmark of Leco. And in 2016 to 2020, we introduced the highly sensitive benchtop MS. And I'll come into more details of this. This is the Pegasus BT, which you see here. So just to go into more detail, this was the first Pegasus, the PEG-1, quite a large instrument. And we moved on to the Pegasus 2, which came out pretty soon afterwards, where you can see there's a big space here, but what they basically did is put the GC on top of the TOF-MS. This bit here is part of the flight tube and the source. The flight tube was big, was very big. But back then, it was quite small. Then we came out with the Pegasus 3. And the Pegasus 3 was a very interesting change for Leco. And the reason for that was that at the time, computers could not cope with the amount of data that we supplied. I mean, it could cope, but it was slow. So you might get a run that would take an hour, but the data processing would take 3, 4, possibly even 5 days. So it was a bit of a struggle. It was great for researchers because they were seeing things they'd never seen before, but they'd only be using the instrument once or twice a week because it takes so long to process the results. And then in 2000, Intel and AMD both introduced the 1 gigahertz processor. And this was a game changer. It was a game changer for the whole world, but it really affected Leco because suddenly we could do data processing that took a lot less. We could do it in hours instead of days. And that was when the Pegasus 3 came out. We then move on to the Pegasus 4D. As was touched upon by Professor Marriott, GCxGC peaks are very, very thin, 0.2, 0.1 of a second wide. And to be able to analyze that, you need a really fast detector. What's interesting about this is the very first one did 500 full spectra per second. Now, bear that in comparison to other instruments, it's miles and miles ahead. It was so fast that they actually slowed it down to 200 because the system still couldn't cope. And it wasn't until later that they returned to the 500 again. But because they could get that speed, it allowed them to analyze those really, really thin peaks of GCxGC. And so along with some persuasion from Professor Marriott, we moved into GCxGC and we brought out the Pegasus 4D. People often ask why a Pegasus 4D. The 4D stands for 4 dimensions. If I can remember the dimensions, you have the first dimension of the primary column. You have the second dimension of the secondary column. You then have the deconvolution of the software itself, which is using the other dimension, so the third and fourth dimension of mass spectrometry. So mass spectrometry is pulling things apart, and then deconvolution then pulls it apart even further and allows you to have all of the information together. You can do GCxGC MS with virtually any mass spectrometry detector. But as to whether you can get the quality where you can do deconvolution and where you can do quantitation and all of these things is very much dependent upon the quality of that information you're coming through and the speed. Speed is absolutely essential. We then came on to the HT, which is a high throughput instrument specifically designed to be extremely robust and could be used in general labs. And then in 2011, as I've already mentioned, the high resolution TOF. Just a quick note on the high resolution TOF. We're not going to do much high resolution over these 2 days, but just an explanation. If you want to increase the resolution in mass spectrometry, what you basically need to do is increase the flight path. And you may have seen some of the mass spectrometers that exist with gigantic chimneys that disappear up into the ceiling. And that's what they've done, is increase the flight path. What Leco did was take a completely different route. And we created the multi-reflecting. And as you can see, it just goes back and forth all the way down and then goes back up again. This is 90 centimeters wide. But when it's at full whack, it does 40-meter path length, which is quite staggering. There's more technology to it, but I'm not going to go into the details. It was just to give you an idea. So it gives an accuracy of less than 1 ppm, which is 0.0001 m/z. So following on from that, we brought out the GCxGC version of that, the HRT4D. And in 2016, the BT that I've already spoken about. The HRT Plus came out, which added to the technology, which, like I said, I'm not going to go into the details of that. And then the BT4D came out. And then last year, we brought out the Paradigm Shift, which is a flow modulator. I don't know, Professor Marriott, are you going to talk about flow modulation?
I'll mention just...
He'll mention it, okay. Flow modulation is an important part, but it's nowhere near as accurate as thermal modulation, but it's useful in certain respects. And we brought out the Paradigm Shift. And then this year, we released the Pegasus BTX, which is the first time we've brought out GC and GCxGC in the same system at the same launch. And it's interesting, I think, looking at this, is that you see the GC oven, and the size of a GC oven hasn't really changed, and that's for obvious reasons. You need to fit your column in, etc., etc. And you can see, just about see the GC oven here or here, and they almost look identical. But look at the size of the TOF in comparison to what it is now. This is smaller than some single quads. It's a huge advancement. On the BTX, we have a newly designed detector. So it's kind of difficult for you to wrap your heads around, but the detector is not inside the vacuum. It actually sits outside the vacuum. And it's a technique called photomultiplier tubes with a scintillator window, where the ions hit a plate that create electrons that create photons. The photons then go outside the vacuum, go across normal atmosphere into another detector, the photomultiplier detector, where they change into electrons, a cascade occurs, and they get an amplification. It's a little bit complicated, but from an engineer's perspective like me, it's staggeringly impressive. It has fast full spectrum acquisition, as we had before, 5 orders of dynamic range, which is extremely important when you're looking at a lot of the complex samples that you're looking at, because you've got those little peaks and the big peaks, and you want to be able to analyze both of them and not be stuck at not being able to see your smaller peaks. Femtogram level sensitivity. So that was a question that came up before about how sensitive you can get. So this is triple quad sensitivity. This is a little bit of a game changer. We didn't realize when we brought it out how much of a game changer it was, because people use triple quads a lot of the time specifically for sensitivity, but they can't do non-target screening. You can only do targeted analysis. So to have an instrument that can get the same sensitivity as a triple quad at the same time as doing non-target screening means things like athletes, etc., can be tested there and then, and we can find stuff out about them that is not necessarily within the regulations already. This happens a lot. Quite into athletics, and I find it quite annoying that they don't use them all yet. We have a stay clean ion source. This originated right back in the early days of the Pegasus. You will come across people that talk about sources that don't need much cleaning, or they stay clean, or whatever. I personally don't like the name stay clean, and I don't like it because it sounds like it's marketing. It's actually a source that does stay clean. It's called an open ion source. We've used them in all of our Pegasus unit mass range from the old days of the Peg 1. And the way it works is that the source ultimately doesn't really have walls. And when you clean a source, what you're doing is you're cleaning the walls. So if you haven't got walls, then there's nothing to clean. So as a result, you end up with a stay clean source, which rather coincidentally and luckily works really well with hydrogen as well. So all of our instruments now come hydrogen carrier gas ready, which if any of you are involved in the purchasing department of your facilities, you'll know that helium is a bit of a pain. It's expensive, it's hard to get hold of at times, sometimes you can't get hold of it at all. So converting to hydrogen and using hydrogen generators, not cylinders, but use hydrogen generators that have automatic switch-off valves, which makes them much more safe. Fully recommend. Like I said, it's the smallest top footprint, and because of this fancy detector we have, it has a 2-year warranty on it. Coming on to the GCxGC side of things, I'm sure Dr. Marriott will go into it in more detail. This is specifically the Leco one. So this is the modulator here. Here we have, there you can see a hot jet. No, that's the cold jet, and that's a cold jet, and then here is a hot jet and a hot jet. This is called the quad jet because there are 4 jets on it, 2 cold, 2 hot. There are different types, but this is the one that we have designed. And here we have a secondary oven. Not all GCxGC systems have secondary ovens. We find it important, as do our customers. They find it very useful. Just as much as with gas chromatography, you have ramp rates in your oven, you also want to have ramp rates in your secondary oven, and you want to have just as much control there as you do in your primary oven, so on your secondary column. So we introduced a secondary oven as well. Coming over here, very difficult to see, and my apologies for that. I'm trying to get a photograph that was easy to do. This is the paradigm shift that I was talking about, a flow modulator. This is the paradigm here that you can barely see, and then the shift. What this does is allow you to use, instead of using thermal cryogenics to do your modulation, using flow, pressures and flows to create the same effect. It's a reverse fill flush. I won't go into the details. And it's completely novel, it's completely unique to Leco. There are other manufacturers that do other stuff out there as well. Another thing that came up within the questions is, what are the limitations? One of the limitations of GCxGC, TOF-MS, is the amount of data is staggering. I mean, it really is phenomenal. We still reduce the amount of data that we create for what we put onto a hard drive. So we put on 500 spectra per second at maximum. You don't have to use 5, you can use 5 if you want. However, the instrument itself actually collects data at 35,000 spectra per second. There is no hard drive out there that can cope with that kind of data, which is where the transient recorder comes in, because it brings that down to something that they can cope with. But still, 500 spectra per second, you're running it for, say, 40 minutes, you're doing it over quite a large mass range, and you want to compare that sample with, I don't know, 100 other samples. That's a lot of data and a lot of data processing. It's really, really hard. So hard that it has taken us many, many years to come up with software that can cope with it. So this is Chromatoph Sync. What Chromatoph Sync does, this takes one-dimensional data, which in itself was hard enough, and allows you to make comparisons using PCA, etc. And then we have the GCxGC, which is Chromatoph Tile. This can take, and there are people around the world, clinicians, that take samples from patients, and they do big data studies to try and find biomarkers, try and understand diseases. And when you're doing this kind of thing, you can't do it with 5 patients. You can't do it with 10. In fact, in the UK, I don't know why this particular number is apparent, but you have to have a minimum of 84 patients. But quite often, you're talking hundreds. So to take all of that data, hundreds of times, bearing in mind quite often your samples are maybe in duplicate, possibly in triplicate. So you're talking in excess of 1,000 samples, and you need to process that data. Now you remember right at the start of my talk, we were saying that one sample took 5 days. Now we're talking about thousands of samples. And what this software is allows us to do that now. It allows you to store the data on a separate drive, so you don't have to try and put it all onto one computer. You can keep it on a server, whatever, and it will still work with it. And you can do all of these wonderful work and analyze and understand what the differences are between your samples. I'll come on now to, this is, I just grabbed some, you can imagine we have hundreds and hundreds of customers. So I just grabbed a few here. So DSTL, they're the Defence Science Technology Laboratory for the UK government. SGS are a big contract lab. Natural Resources Wales, I'm not going to attempt to say the Welsh name. They look after the country of Wales water under the Water Framework Directive set by Europe, where they look at hundreds and hundreds and hundreds of pesticides, of pharmaceuticals, etc., that are in the water to make sure the water's clean. And toxins come in that they don't know of, which is again where non-target screening is absolutely essential. Water is quite a complex matrix. This is the logo for the Thai National Army, I believe. We have the US Army, the US Air Force, Nestle do a lot of work with us in a thing called MOSHMO, which is mineral oil contamination in your food. This comes from cars, it comes from lubricants inside the factory. It's carcinogenic. L'Oreal, I'm sure many of you are familiar with. Space Park Leicester, they're part of the UK Space Agency. They have systems for testing breath analysis. This is the fire department of Italy. They use it for forensic analysis of arson and to understand what has caused fires, to potentially use in court to convict people. CFAS, they're another arm of the UK government that do the analysis of marine. So they're looking at oil spills, for example, or understanding what's going on in the toxicology of not just around the UK waters, but they travel all over the world, helping understand what's going on with the various waters. FERA, I've not touched them. That's the Food and Environmental Regulatory Authority. And they look at food safety and pesticides, etc., in the food for the UK, although they have a lot of influence across Europe as well. So going back to this particular slide, because the BTX came out, I thought it was about time we had some more photographs taken. So very nicely, Slava got his tie out, and we have them with the BTX. But I also thought it was important to understand that these guys have been a kind of cornerstone for Leco, but they're not the only people. There's a massive team of people that work behind them and work with them. And so a few more. So we've got Slava here, and then Matt Soik, who is the main person to design the BTX. David, who is instrumental to the software side, to GC Tile and GC Sync, and then back to Kevin again. I wanted to keep mine fairly short, fairly brief, so I hope I've covered as much as I can. If you have any questions, then please go ahead. Thank you.
Thank you so much, Alan. Thank you for your time. Thank you for your presentation. We have some questions as well. As we mentioned before, if you have any additional question, let us know. Tomorrow we will have these questions answered as soon as we have the Dr. Philip Marriott lecture. We will make him work at night, so he has the Australian time, so he can do it. And some questions for you, Alan. How do Leco instruments accelerate analysis times without compromising data quality?
Oh, that's a good question. Ultimately, it comes down to chromatography. So chromatography is, the slower your chromatography, the more separation you will get. And so when you speed things up, it can become a little bit more difficult. The key to success is there's twofold really in the modern world, is by being fast. If you've got a fast detector, that enables you to really analyze those peaks as they're coming through. So you can get much greater separation because you've got more data points between those two peaks, so you can make much greater analysis. Also hydrogen. Hydrogen is far faster than helium. This enables you to do much faster times. I haven't gone into it, but as an example, we took the ASTM 8270 method for semi-volatile analysis in water. And that's typically about 32 to 35 minutes for an analysis. When we optimized it for hydrogen on our instrument, we got that down to about 8 minutes. And so ultimately, it just comes down to the speed of the detector and making sure that you've got optimized chromatography.
Thank you so much. Another question about from the voice of the customer, from the customer perspective. What do they say about the software and the interface or the interaction with the software and the machine?
Naturally, I'm biased.
Sure.
But I haven't just worked for Leco, I've worked for other companies. I've worked for Waters, I've worked for Micromass. I used to build magnetic sector instruments that would take about 6 months to a year to build. So I've been around, I've seen the Agilent software, Thermo software, and I can easily say that the Leco software is very, very user-friendly. The example I normally like to give is a guy called John Quick. John Quick is the principal chemist for ALS, which is the Australian Laboratory. What does the S stand for? Systems, I think. Service, that's it, the Australian Laboratory Service, but he's the principal scientist in the UK. And he wanted to try our equipment out, so we lent him one for a couple of months. I went down there. It was quite close to where I live anyway, so it was easy for me to access. And he was very pleased he was there. We trained a couple of his lab technicians. He has a big lab with about 30 GCMS in it. And the following week, I phoned up the lab to see how things were going. And they said, oh, we're not working on it. And we're not working on it because UCAS, the UK Accreditation Service, have been in and say that we need to do some work before we can complete our accreditation for this year. So everyone in the labs is working on the UCAS work, and no one's working on the instrument. I'm panicking because I'm like, you've only got this instrument for a short period of time, and no one's using it, so you're not going to be able to test it and understand it. So I said, so what are you doing? How are we going to do this? And they said, oh, don't worry. Our boss, John Quick, he's working on it. Immediately I panic because I've not trained John. So how's he supposed to use it? So I just say, okay, don't worry, I'll be there. I live 40 minutes away. So I just jumped in my car, drove straight there. John came to see me and he said, what's the problem? And I said, well, I need to train you on the instrument. And he said, oh, it's okay, I'll finish the work now. And he had taught himself how to use the instrument, how to run samples, how to acquire samples. He hadn't taught himself how to do the data processing, but he transferred that to his current data processing system. The point being that it's such a simple piece of software. And you can find, I think even on YouTube, there's an interview with John, where he says, converting from single quad to TOF just couldn't be easier. With single quad, you have to build windows, You have to make masses come up at certain periods, etc., etc. With TOF, you just turn it on and run it. And then it's the data that you really have to work on. So he managed to use it completely himself without any training. So I am biased, but it's fairly straightforward to use. Very user-friendly.
Awesome. Thank you. And final question. And if you already have a GCMS instrument with a simple quadrupole, can it be switched to GC times GC? And if so, what is it required to make?
Yes, is the simple answer. A single quad can do GCxGC. But what you must always remember, as I've spoken about before, is that a lot of it comes down to speed. So what a single quad does is it filters. So a single quad only looks at one mass at a time. Now you might look at two masses, but what you're actually doing is flipping from one mass to the other very, very quickly. So what time of flight does is look at all of the masses. So if you're looking at one mass with a single quad, and then you look at two, and you're doing that by flipping from one to another, you've just halved your sensitivity because you're flipping between masses. And so you have issues with that. Also, because you're only looking at one mass at a time, as you're going across a peak, the mass that you're looking at is changing as you go across a peak. So you get this cool thing called skewing, where as you're starting on coming onto a peak, and the lower mass hits, by the time you get to the higher mass, you've actually increased the size of your peak because you've gone up. So your mass, detection of the higher mass is going to be greater than the detection of the lower mass, even though it's the same mass spectrum. So you get this skewing effect. So it makes it much harder to do decent deconvolution and good deconvolution. It can be done. You can use single quad. There are plenty of people out there that use single quads. There are some manufacturers now that have very fast single quads. Just always bear in mind, it's like many things in life. If you go for something cheaper, then you'll get a cheaper result. If you go for something more expensive, you'll get a higher quality result. And one thing to take into account, time of flight works at a much lower vacuum than single quad. So time of flight will always be more expensive than single quad because you need to have a much better vacuum system. So not only do you need a stronger vacuum system, you need stronger structure to be able to hold that vacuum, etc., etc. Does that answer?
Okay. Thank you so much. Thank you so much, Alan. Thank you for your presentation. And I think that's it for today. Thank you for you. And let me switch to Spanish. So let's give a big applause to Alan. Ok, nada más vamos a hacer cambio de presentador. Denos 2 minutos para que el siguiente presentador es Thiago Esquena y denos 1 minutito para hacer el cambio.
Is Thiago on this?
Yes. Thiago is the next week. You have your laptop?
Yeah. Oh, your laptop. I'll leave this with you.
Yes, sir.
See you.
Thank you. See you. I thought this was the HDMI. It's this side? Yes, sir. It's here. Oops, wait. Sorry. Sorry. This is a regular USB? Okay. Oh, for the pointer? Yes. Do I need that? Do you want to use this one now? Or do you want to move around?
I think I will be here. Yeah, I think you keep only that one? Huh? You keep only this one? Okay, I think it will be fine. Is the battery already plugged? Hmm? The battery is already plugged? Yeah. Okay. I do need because this computer.
La introducción de nuestro siguiente ponente. Como decíamos, Thiago Esquena, viniendo de Brasil, él es nuestro ingeniero de aplicaciones y voy a hacer una pequeña semblanza de él. Tiene amplia experiencia en cromatografía aplicada a matrices complejas, con formación en química industrial y un doctorado en química. Ha trabajado en técnicas avanzadas de extracción y caracterización de productos naturales y petroquímicos. Actualmente se desempeña en Leco Instruments como investigador postdoctoral en la Universidad Estatal de Río de Janeiro, enfocado en la caracterización química de contaminantes ambientales. Su experiencia abarca desde el análisis de tequila hasta productos petroquímicos, lo que lo convierte en un experto ideal para abordar diversas aplicaciones. Démosle un caluroso aplauso a Thiago.
First, hello for everyone. So my name is Thiago Esquena. I will try to present for you right now some applications. The idea right here, I will try to focus a little bit on the introduction, but the focus here, the main thing, it will be the applications. So how we can use our GCxGC system to...
Okay. Sorry. Okay, better? Sorry. I will show some applications right now, okay? Because Professor Marriott told a lot about the introduction, so everyone already know a little bit about GCxGC. So I will do a little introduction, and then I will show a little bit about GCxGC in the introduction, columns, how we can choose or pick our columns, the modulations that we work here at Leco, our systems, our TOF-MS system, and of course, the applications. So as Alan already told us, Leco is well known by the elemental analysis. We work also with material characterization, microscopy, imaging analysis, and the focus on this presentation will be the mass spectroscopy. So here is a quick view of our system. So here is where we insert our sample. Here we have our first dimension column, second dimension column, and the modulator, and here we have our detector. Here is just to show how where is located our modulator, the secondary oven, and here we have our primary oven. When we have our first dimension column, the second dimension column is inside this the secondary oven, and here we have our modulator. So we can work with different temperatures over the first dimension oven and the secondary dimension oven. So just a quick view about the technique. So in 1D GC, in this example, we could analyze 5 different peaks. So, and we are, as we can see here, they could be like good peak shapes, but we don't know what if there are more compounds that has the same retention times, for example, as this blue one peak. So that's why we have GCxGC. So at the end of the first dimension column, we have the modulator. Then we have the secondary column when we have the secondary separation. And in this time, we can notice that this red peak right here is composed by, is a coelution, which means that these 4 compounds has the same retention time, or very, very similar retention times. So that's why we have the GCxGC. So all these compounds could be separated in the secondary column, in this, our secondary dimension. So what we can see here, for example, we can see that these same compounds has the same or similar interaction with the first dimension column. So they have the same or similar retention times in the first dimension column, in the first separation. And they can have different interactions with the secondary column. So we can actually separate them into this GCxGC space. The same thing right here we can see from the other peaks that we, in this case. So in 1DGC, we started with analyzing just 5 peaks, and using GCxGC, we increased the power of separation. So in this time, we could see like 17 peaks. So we increased the peak capacity, which is we can see more compounds, mainly because we can separate all these compounds properly. And we have like a good identification of these compounds. So here is how the system works. So for example, we have here 1D separation. So it's the effluent that is the peak that is coming from the first dimension column. So this peak will be sliced in different small chromatograms. Each one of these chromatograms represents the separation that we are getting in our secondary column. So what our system does, they will put all these small chromatograms side by side, and we can see the 2D visualization, 3D visualization, and we can call it contour plots. So here is an example of a sample. So as we can see here, for example, we have tons of peaks that has the same first dimension retention times. Because here in the x-axis, we have the first dimension retention time. The second axis, we have the second dimension retention time. And we can see the colors. The colors means the intensity. So in this case, more the reddish color means more intensity. Green and blue, less intensity. So how I was saying, we have right here a lot of peaks that has the same retention time in the first dimension column. So they will be coeluting in your first dimension separation, in your 1DGC. Here we can see the 3D visualization, where the z-axis, is the intensity. So a little bit about columns. So columns, we need to think in separation. I do like this picture. So we can see like non-polar types of columns and like extremely polar columns. So we have tons of different possibilities to work, and different polarities too. We can see here that we can work as using a conventional column set, where we have a polar column or non-polar column in the first dimension, and in our secondary column we have a polar column. We also can work in the reverse phase column set, where we change, so we have a polar column in the first dimension and a non-polar column in the secondary column. So as we can see here, when we are using like apolar columns, we can separate most of the main separation is that we are doing is mainly because we have like the boiling point. And we have, if we are using polar columns, we are separating our compounds through their polarity. So, okay, how can we choose our columns? Because we have tons of different columns. We can play with column sizes too. So how we can work with that? We go to our literature. There are a lot of different papers already published. There are a lot of different researchers doing like their best to have like a good separation, improve the chromatogram quality. So this is a go-to start. And also, it's you guys know your sample. If you already work with 1D GC, you don't need to like start with a different column. You can start with your column that you already worked, and then change your secondary column, for example. Okay, so about modulation. So modulators are the heart of the technique. They work in three ways. They collect, concentrate, which is like focus, and reinject. So here are our thermomodulator. First I will talk about thermomodulator. So thermal stands for, we use temperature in order to trap our compounds. So here we have our thermal modulator. So here we have our cold jets, and right here our hot jets. So how this works? In the first moment, we have our cold jet on right here. So our analytes will be trapped in this column section, while we have right here our second hot jet be on. So we are releasing all the compounds that were collected, trapped in this column section, into our secondary column. After that, we have a hot jet on, where our compounds will be directed into our secondary cold jet, and they will be trapped again. So we always have a cold jet, hot jet, always playing, so we can trap our analytes properly. So we can work, at Leco we have two options to work with thermomodulation. One is using cryogenic. So I always like to pinpoint some benefits and some disadvantages. For example, the benefits, cryogenic modulation is like the most important one, because we are working in extremely low temperature. So this hot jet is so cold. So we can trap even the low boiling point compounds. Some disadvantages is the expensive. It's a little bit expensive due to the maintenance, because sometimes it's difficult to get liquid nitrogen. when I was in Brazil, we had a GCxGC system in northeast of Brazil. It's too hot. So when we buy liquid nitrogen, it was like from another state. So until that liquid nitrogen gets into my lab, if we buy like 100% cylinder, it will arrive at our lab like 70–60%, because we are always losing part of the liquid nitrogen that we bought. About benefits, this is also very, very important. The peak width of our compounds. So the lower that they are, better separation. So this is a go-to modulator. So we release also a cryogenic-free modulator. So I need to say that the best benefits is not rely on liquid nitrogen. So in this case, the disadvantages of this modulator is trapping the low boiling compounds, the VOCs, because the temperature here, here we, instead of using liquid nitrogen, we use compressed air. So you just need an air compressor to work. That's the great thing. So we can work independently of liquid nitrogen. But the disadvantages is the trapping, because this temperature is higher than this one. So sometimes we cannot trap properly some compounds. So, okay. We also have flow modulators. So here we have flux. It works in two different ways. We have the divert mode and inject mode. During the divert mode, the helium will be directed. So here is the normal flow from the first dimension into the second dimension. So in the divert mode, we have like higher flow helium coming into this region. So it blocks the normal flow path. So we have this flow going into the waste. In the inject mode, we have the helium being direct into this region. So all the analytes that were in this this area, plus the compounds that are coming from the first dimension column, goes into our secondary column. Okay, again, the benefits, it is less, it's more cheaper, especially if we compare with the liquid nitrogen one, because here it's, you don't need like the liquid nitrogen peak, because in order to maintain your liquid nitrogen in a proper temperature, you need bigger tanks to avoid this loss. So here I can pinpoint that it is compact. And the peak widths are very similar to our cryogenic modulator. Disadvantages, as we could see right here, we lost part of the analytes here and the waste. So we need to work with higher concentrations. So this is a to-go modulator when you are working in a petrochemical, for example, because you have like for quality control purposes, because it's very reproducible. And here we have our reverse flow flow modulator. We call it Paradigm. So how it works? We have our effluent coming from the first dimension column. These compounds will be sampled in this loop. Then, in the injection step, we have the helium, for example, flow coming into this region where we can flush everything that was inside here in this loop into our secondary column, and we have our separation. So benefits, again, I can pinpoint about the expenses, especially when we are comparing with the liquid nitrogen one. It is compact. Comparing with the flux, this is very good. We are not losing any compounds. And we can work with dual detection here. So some disadvantages. It has larger peak widths, especially for the low molecular weight compounds. And it has like higher second dimension flows right here, because we have like this back pressure. We have a higher flow of helium or hydrogen, and that's why we have our shift. So we can split part of this effluent that was accumulated right here into our other detections. So we can work with TOF-MS and FID. So here is our shift. So here is the analytical column, and that is coming from the secondary column. Here we have the column that will carry all the compounds into the TOF-MS detector, and here for the FID. So it is like a novel pressure-assisted flow splitter. This is very important. It maintains constant MS flow and split ratio between MS and FID throughout the entire run, even during open ramps. So because we have these pressure controllers, so we can keep our split ratio between these two modulators always the same through the analysis. This is very good. So in this case, we can have a configuration when we have GCxGC, TOF-MS, and FID. When we need to use our paradigm shift, or for just FID applications, we have our paradigm. Detectors. So the detectors are the eyes of our system. So here is how our detector works. So here we see the ion source where our masses will be formed when we are fragmenting our molecules, and we will produce our mass fragments. These mass fragments will be accelerated into this flight tube, which is our analyzer. So we have our compounds will be separated into this flight tube through their mass. So low fragments will arrive here at the detector first, and then we have our higher boiling point. We have our bigger mass spec fragments. Some benefits. We have the complete analysis of our compounds. We have all the mass spectrums are collected. So here is an example. I think this is very nice. Here is a nice view about our spectrum deconvolution software. Here we need to imagine here is a peak in green. This is not a good picture, but here we have a huge peak in green. Here we have a small peak in orange and other small peak in blue. And as we can see here, they have same first dimension retention time and slightly different second dimension retention times. And as we can see here, each one of these peaks has a unique mass spectrum. This is the power of the spectral deconvolution. We can see these slightly differences thanks to our system. And another important thing that Alan also mentioned is the higher acquisition rate. In order to have like a good spectrum deconvolution and have like good peaks, we need like higher acquisition rates because these peaks has like 80 milliseconds, sorry, 50, 100 milliseconds, so they are very, very short. Some disadvantages, especially when you are comparing with quadrupoles, it is less selective, mainly because the way, as we can see, the way that this detector works. So for quantification purposes, our equipment can work in ppm, ppbs. It's comparable to a single quadrupole, for example. Here are our high resolution system, as Alan showed. All the fragments will do like this kind of zigzag inside here. So we have like high, they will procure a long distance, so we can have more resolution power, and we can have like values. We can have mass spectrum such these ones. So we can have right here, we could acquire with 5 decimals in our HRT system, and in our Pegasus BT system, we are already working with 2 decimals. So here are our 2 systems. Here are Pegasus BT. It works both GC and GCxGC, both systems. So this one, the main differences between these two. Here is we have just one. We can just work with electron ionization as our in our ionization chamber, and here we can have besides ionization impact, we have PCI and negative, positive chemical ionization and negative chemical ionization too. So let's talk about applications. So this equipment can be applied in several different areas. So from energy fuels, environmental, forensics, toxicology, food and aroma, metabolomics, and natural products. I will talk about like a few of them. So I will start with environmental analysis. In environmental analysis, we have like tons of different molecules that we are trying to find. So there are from pesticides, pharmaceuticals, we have sulfur-containing compounds, nitrogen-containing compounds. There's like tons of different compounds that we are interested in. And the environmental samples are very, very challenging because there are the matrix is also very complex. So here I will show you guys a work that we've been doing with Professor Karin van Meulen. She is from Rio de Janeiro, Resende. And we decided to work with fast GCxGC. So instead of just working with regular GCxGC, we decided to work with fast. So in this case, we have like, we need to use columns, long length columns. For example, here we are using 10 meters. And in this first work, we decided to analyze endosulfan metabolites in doing like a quantitative analysis in several different points in this river. So we take this standard mixture, the EPA 8081 with 22 pesticides. We also acquired 3 other endosulfans. We got this linearity. So from 1 to, we decided to use our calibration curve from 1 to 50 nanograms per milliliter. We calculate intermediate precision using lower, intermediate, and higher points of the analytical curve. We do selectivity, extracting our matrix, taking one sample and extracting this sample tons of times. So we have like our matrix. And we calculate the LOD and LOQ. So we collect 6 different points in this river, and we use catchers. So here are the our standards. So they look like this. So we have analysis, a very, very short analysis, almost 12 minutes. And we got like good results in linearity, selectivity. So we spike our matrix that was previously extracted with our standard mixture. We have like good results. Any other peak was like co-eluding as expected because we are using GCxGC. Here are some LODs and LOQs. Here are the most values, the lower values and the higher values that we find for LOD and LOQ. Intermediate precision, we have 2.4 to 5. Here we have like some of these compounds had like not so good result at this point, but the paper I think is already being published. So we rerun all these things and we got results from, again, from 2.4 to 5. So we have like extremely good results using like GCxGC for this quantification. So here are these where we collect the samples. So we divide it in quarters. So for example, here at these points, we have the most intense compounds that were found. So endosulfan has higher amounts in this region, while lactone endosulfan in this region, and beta BHC in this region. Another important thing that we need to notice, the focus on this work was the pesticides. But as we acquire everything, every single part of our sample, all data, we can also see other contaminants in this water. So we could find some compounds that belongs to pharmaceuticals, cosmetics, other types of pesticides too, and some food derivatives. We have also worked with qualitative analysis now. So we took some samples right now for the water treatment plant. We have like the sludge. We extracted that sludge and we analyze these extracts through GCxGC-TOF-MS. Why we decided to analyze this sludge? Because in Brazil there are some of these water treatment plants that are disposing these sludges into landfill, no landfills, in farmer regions. So like land, like a little bit of, like, because they think it's just earth that is in these samples. So again, we use catchers to separate this, to extract these pollutant compounds. We, again, we decided to work with fast GCxGC. So again, run very, very short, like 20 minutes. Here are conditions. And in both cases, we are using cryogenic free modulator. So it's all this data that I just showed you is from the cryogenic free. So we can see right here that we have good peak shapes through all our chromatogram. So here are how it looks like one of these samples. We have tons of different compounds. So in this region, we have low boiling point compounds. We have some aromatic compounds, especially right here. This line right here came from the hydrocarbons, linear hydrocarbons. Right here we have cyclic hydrocarbons, olefins too. In this area we have these big, huge peaks coming from the free fatty acids that is present in our samples. And what shocked us the most, was the hormones content that we found. So this region right here and right here, we have like wraparound, is the area, the region of the hormones. These hormones are coming from both fetal hormones and hormones from people. So here are the qualitative analysis. In this first picture, we can see the number of the tentatively identified compounds, which means these tentatively identified compounds, we just compare the mass spectrum of what we obtain with the mass spec library. So we just use the similarity search. So our chromatogram presented to us, we data processed our raw data, and we obtained almost 4,000 peaks. And for these 4,000 peaks, we tentatively identified 337. So this 337 represents almost 60% of the total area of the chromatogram. So we could identify like most of the compounds present in our sample. And as we can see, hydrocarbons are the main ones in the sample. The majority, followed by aromatic hydrocarbons right here. We have tons of free fatty acids and alcohols. Another way to see the counterplot is do this picture. We call it scatter plot. When we remove, for example, the intensity of the peaks, and we just see where are the peaks in our chromatographic space. So right here we have in these brown circles, we have our hydrocarbons. Here we have some aromatic esters. Here we have our free fatty acids. We can see some of them here in these blue circles. And here we have our hormone derivatives. So as we can see here, we have a structured chromatogram. What does that mean? You cannot find, looking into this picture, you will never find a hydrocarbon, linear hydrocarbon in this region, because the hydrocarbons will interact with first dimension and the second dimension, way different from this compound, for example. So we have structured chromatograms. So we will always know if we are using, for example, a apolar column, non-polar column, polar column in the second dimension. We always see the hydrocarbons line right here. After that, we have the olefins, cyclo olefins, aromatic compounds, nitrogen, sulfur-containing compounds, right in this region. So again, we found a lot of different compounds that are very interesting, like pharmaceuticals, food derivatives again, tons of hormones. We found a hormone that could be like biomarker for human contamination with our homes, for example, and pesticides again, and polycyclic aromatic hydrocarbons, PAHs. So as we can see, all of these compounds will be put into a land where crops will be like harvest. So all of these compounds will migrate into our food. So the main importance of this work is to show that we cannot put this type of residues in our lands. We need to treat them. Okay, I think it's the most popular case is the petroleum analysis. So GCxGC is go-to tool to have. So we have several different compounds that we're interested in. We need to check if our, for example, gasoline has sulfur content, nitrogen content in order to avoid pollution. And several other species that can change the calorific value of our petrochemical products. Here are a very nice work where they decided to do a quantitative analysis and change the, use the two ways, the two column sets, a reverse phase column set and a normal phase one, to see how this could affect our quantification analysis. So the sample was diesel, was diluted in dichloromethane, and here are some compounds that were used for the quantification, analytical curve, normal phase. Right here we have apolar column, polar column, and reverse phase, polar versus apolar. So here are the counterplot that they got. As we can see right here, we have the paraffins. They have like this tailing effect in the secondary dimension, and this tailing can affect how we can see the other compounds. But they did not decide to change any other parameter. They decided to stuck in 2 degrees Celsius per minute because it was like a recommendation. It's a normative that they are following. So they decided not improve this chromatographic separation. So they changed the column set. So we have right now a polar column and a non-polar column in the second dimension. As we can see, we still have this kind of tailing effect, but this tailing effect is not affecting this aromatic area, because if we have our linear hydrocarbons in this area, all these peaks from this region are our aromatic compounds. So as I can see, this tailing effect is not affecting these compounds. So we have like a better separation here. Also, as we can see, we have like a good roof effect, which means that, for example, if this main peak right here is C16 hydrocarbon, if we follow this line, all these compounds right here also has 16 hydrocarbons. That's also very, very important information for that we can get from GCxGC. So the correct quantification results are in this table. We have the normal phase approach, reverse phase approach, Here are the compounds that they are monitoring. They divided them in classes. So as we can see here, there's like no differences between these values. But here are the important thing. As we can see, in the normal phase, we have higher standard deviation. So here we don't have like a good result, a good quantitative result. While in our reverse phase, we have the values are lower, so we have like a good quantitative analysis. Also, the mass spectrum, as we can are talking about compounds that has like similar mass spectrums, this tailing effect can also make some make our system, our detectors, confused, because we have more noise near our peaks, so we can reduce the identification, where the similarities will be lower. So the best chromatographic method was the reverse phase for the quantitative analysis of this diesel. Now I will talk a little bit about forensics. So forensics also is very, very different area. We have tons of different compounds. There are some compounds that we need to derivatize in order to be analyzed via GCxGC. So there are several different types of compounds. So here is a nice paper. It was made by Kathleen Barreau and Pierre Hugues Stefanuto. Kathleen is well known in GCxGC field for have like good papers on forensics analysis. So in this one, she worked with our HRT, and they work with non-polar polar column set. So let's talk about a little bit about the sample. In this case, it was like a murder case. They found someone in the woods near the house, and the police gave to Caitlin the samples. So it was a man, 79 years old, caused the death. They said, firstly, like natural causes, like heart stroke, and they give to her 3 different types of samples. One right under the body, one when in the adiposity, that it is near the cadaver, and the edge of the cadaver, we called decomposition island. So here, all the grass that was here died because the chemicals that our body is expelling. So they made SPME analysis in each of these points, and here are the data. So here are the adiposity counterplot. Here are the under the body. Here are the edge of the cadaver decomposition, and here are the control. It's like a blank. This blank was taken 10 meters away from the body, so we can see how all the chemicals, all the compounds that are in this region. So as we can see, these samples, the edge of the cadaver and the under the body, are very, very similar to the our blank, and the sample that caught the attention is the adiposity. So here in this sample, we need to identify our biomarkers. So here are the Fisher ratio analysis. So here are the adiposity under the body and the edge of the cadaver. So as we can see, the adiposity samples has higher values of Fisher ratio, so they are the ones that we need to focus. Here are the dendrogram and heat map, where we can see which kind of compounds, for example, the adiposity has, and the other samples don't have. So for adiposity is like the most complex one, so it has like all the other classes and basically the other samples doesn't have. So here in this table we can see the identification of the main compounds, the structure of the main compounds that has the highest values on the Fisher ratio. So it was identified using retention index, comparison between the mass spectrum obtained versus the library NIST, and also we could use, they used chemical ionization data in order to obtain the molecular weight of each one of these compounds, in order to improve the identification of them. And here we can see the peaks when we use a filter is like a function in our software when we can remove some compounds. In this case, this is the adiposity sample minus all the compounds that are present in our blank. So here are all the potential biomarkers that we can use for these purposes. Right now, we will focus a little bit about natural products. Here, we have like, we are interested in sesquiterpenes, monoterpenes, free fatty acid if we are talking about plant extracts. So we have tons of different compounds. There are some plant hormones. So also is a very, very complex matrix. In this paper, they made a comparison between GCxGC QMS versus GC QMS and GCxGC TOF-MS in order to characterize this sample, this plant, the essential oil obtained by this plant, and test this cytotoxicity activity. Here are the conditions that they are used. Again, for the GCxGC purposes, it was a normal conventional column set. So here are the results. As we can see here, we have the 1D chromatogram. We can see a lot of peaks that are regions with higher coelution. We have right here the sesquiterpene regions, the monoterpene region, and we have these like peaks that we cannot identify. While in the GCxGC, we can see the plurality in each one of these regions. Right here, for example, we have here like a bad separation, and here we can identify some peaks that has like very, very similar second dimension retention times. So in the first dimension analysis, they found 41 peaks, but just 7 were identified. So here are all the classes of these 7 identified compounds. And as we can see, we have like tons of coelution and peaks, bad peak shapes, low resolution. While here we have 213 peaks in the GCxGC analysis, and they could identify 80 peaks. So we increased almost more than 10% of 100% of our capabilities. More than 8 times. Sorry. So in this case, we could find some other types of compounds that we could not find here. So, for example, the classes of monoterpenes we could not identify here, as well as sesquiterpenes. And so, as we can see here, we can understand why that happened. For example, the monoterpenes, they are in low concentration, so we need to increase their intensity. And we can see here even that increased intensity in 1D separation, we will have a lot of coelution. These sesquiterpenes are this region right here, and they are coeluting with phenylpropanoids. That's why we cannot see these sesquiterpenes in the 1D GC analysis. So as we can see, we increase the resolution. So for example, right here we have alpha terpineol, where in GCxGC analysis we could find this peak with 93% of similarity, while in GC QMS with 58. About this cytotoxicity, this essential oil has activity against tumor cells, and it not kills like non-tumor cells. So it's very, very good results. And in the literature, the compounds that have these kind of activities are these compounds, and they could they could just be found through GCxGC analysis. I think, do I have time? No? Yeah, I think I feel like being happy to talk about these applications. I think I will stop right here, but I am free. You can always be, you can have a nice talk to me. I can talk about all the other stuff that we are doing at Leco. So yeah, thank you for your patience, and of course, if you have more doubts, please.
Thank you. Okay, thank you, Tiago. Thank you so much. We only have time for one question, so if you can please help us. And in this case, would be about petroleum and energy, and it's a mix of two questions. How does GC times GC improve the analysis of complex petroleum fractions, such as crude oil and refinery products? And how can you monitor petroleum contamination in soil and underwater or groundwater? Do you want this or do you?
Yeah, in petroleum analysis, I think GCxGC is a must-go technique, because without it, we cannot have these like nice separations right here. Actually, in the industry, they need to find the amounts of each one of the compound hydrocarbon classes, for example, paraffins, naphthalene, aromatic compounds. So our software also has a great it has like a very good separation and quantification of these compounds, where we can highlight, we can counter these compounds these different classes of compounds, and we can quantify which compound that is in that area or in that region. So it's very nice for the petrochemical industry, because they need to like fast analysis, and GCxGC has like a good application in the petrochemical field, and and also we have a good collaboration with a professor where we are studying oil spills in Brazil. So we are monitoring in several different regions in Brazil, and the idea is to find biomarkers in order to discover which kind of industry or where this petroleum is coming from. So GCxGC is the best technique for this, for example, the petrochemical purposes.
Thank you so much, Thiago. Thank you for your presentation. Ahora bien, estamos ya por finalizar, nos falta la última sesión, entonces vamos a tener un break de 10 minutos, por favor, a más tardar a la 1:10, regresamos a la sala y terminamos con nuestra sesión. Muchas gracias.
Awesome, Thiago. No, why not? You said only once, but that was great. And you were like, oh my goodness. You remember that you were saying that you cannot say impact, but you should say, what was that? No, but that was great. No, what? Thank you so much. Did you like it? Don't be so hard on you. No, but I think that's standard. inicio a nuestra cuarta y última plática del día de hoy. Muchas gracias. El día de hoy nos acompaña como último panelista el doctor Omar Amador. Voy a leer una pequeña semblanza de él. El doctor Omar Amador Muñoz es investigador titular en el Instituto de Ciencias de la Atmósfera y Cambio Climático de la UNAM y pertenece al Sistema Nacional de Investigadores Nivel 2. Su experiencia se centra en el estudio de aerosoles orgánicos atmosféricos y el diagnóstico de contaminantes atmosféricos no regulados, desarrollando tecnologías más limpias para su medición. Con más de 60 publicaciones científicas internacionales y patentes tecnológicas, ha coordinado múltiples proyectos de investigación en este campo. Démosle un caluroso aplauso para recibirlo el día de hoy.
Muy bien. Bueno, pues nuevamente bienvenidos. Muchas gracias. Esta es la casa de todos, ¿verdad? La casa de la nación. Y pues agradecemos a quienes nos acogieron, a Leco también, doctor Mario, por compartir su conocimiento. Bueno, y ahora les voy a hablar de un área, de una matriz que no se ha mencionado, pero que es pues súper importante, porque es el aire que respiramos a diario. Entonces, lo que voy a hacer es justificar el trabajo, comentarles que es una mezcla compleja, los pocos trabajos que hemos desarrollado aplicando esta tecnología fantástica en esta área, y mostraré la colaboración que se tuvo con el doctor Mario. Ese es lo que vamos a hacer. Y no los voy a entretener, espero que hayan tomado café, estirado y etcétera, para que no se me duerman, ¿ok? No se vale. Bueno, entonces vamos a comenzar. Miren, esta diapositiva muestra que nuestro aire está contaminado en el planeta. El 90%, ¿ok?, del hábitat o el 90% o más del 90% de la gente en general, de la población mundial, está respirando contaminantes con concentraciones superiores a los que indica o señala o sugiere la Organización Mundial de la Salud. Entonces no hay aire limpio ya en el planeta. Se han encontrado endosulfán en los polos, carbón negro emitido por quema de biomasa, que permanece bastante en la atmósfera, y entonces con los vientos llegan a los polos, orgánicos persistentes, es decir, las zonas pristinas pues ya no existen, o son muy pocas tal vez las que existan. Hemos encontrado plaguicidas, organoclorados y retardantes de flama en el cráter de Toluca, en el Nevado, por ejemplo. ¿Cómo llegan ahí? Pues por el aire, ¿verdad? Ahora, de esta cantidad de contaminantes, solo algunos están normados, algunos están regulados. Bueno, entonces hay dos tipos de contaminantes. Ese es un mensaje que quiero que se lleven a casa, que son los primarios, que son los que se emiten a la atmósfera, ¿ok?, por una variedad de fuentes, y que generalmente son los que se regulan. Se regula la empresa, el vehículo, como ustedes pueden ver, los que vivimos acá sabemos que ese es nuestro padecimiento, hay que verificar para poder pasar la regulación y poder circular, pero es una emisión primaria. Están las quemas de biomasa, las forestales, las agrícolas, cuando hacemos nuestro huevito en la mañana, la quema de butano, de propano, que por cierto déjenme decirles que es el mayor orgánico volátil en México, en la Ciudad de México, el propano, ¿ok? Y es un precursor de ozono, por ejemplo. Ahora, una vez emitido el contaminante en la atmósfera, hay procesos generalmente de fotooxidación. Ustedes saben bien que en Ciudad de México padecemos bastante frecuente episodios de ozono, alto ozono. Y eso es un oxidante que ataca al hidrocarburo para formar otros orgánicos que se les llama secundarios. Ahora entonces sabemos un nuevo concepto. Contaminantes orgánicos secundarios se forman en la atmósfera. Los contaminantes primarios se emiten a ella. Y entonces ahora se hace más complejo, porque tenemos no solo los primarios, sino los formados. Este es un ejemplo de un pulmón limpio, no sé si exista, sano. Este es el diámetro de un cabello humano, 50 micrómetros, 80 micrómetros, y nosotros estudiamos partículas de 2.5 micrómetros que se impactan en pulmón. Si son más pequeñitas que 2.5 micrómetros, por ejemplo, 1 micrómetro, traslocan a torrente sanguíneo por los sacos alveolares, que son los que intercambian el oxígeno y el CO2. Entre más pequeña sea la partícula, más profundo llega. ¿Ok? Esto es fase particulada. Pero ¿qué tal los gases? Esos traslocan directamente. ¿Ok? Este es un ejemplo del efecto de la partícula. Esto es cáncer, alguien que ha fumado. Este es otro tipo de efecto. Esto es fibrosis quística. ¿Ok? Acartonamiento del pulmón. Es otro tipo de muerte. Y este era un muchacho de 25 años que trabajaba en una mina de carbón. Todo está obstruido. ¿Ok? Por ejemplo, la asbestosis tiene un problema de cáncer de pleura. El silicio, gente que trabaja en las minas le da silicosis, etcétera, etcétera. Esto es ahogamiento. ¿Ok? Deja de funcionar el pulmón. Y solamente están regulados o normados, de acuerdo a la OMS, 6 contaminantes, solamente 6. En la normatividad mexicana incluimos al plomo, aparte de estos. Entonces, podemos ver aquí que son las partículas menores a 2.5 micrómetros, les llamaremos PM2.5, PM10, y estos son gases. Es el único formado. Estos son emitidos, son primarios, y esta es una mezcla de primarios y secundarios, pero solo 6. Hay límites anuales, hay límites en 24 horas. Por ejemplo, cuando el ozono se eleva por arriba de un valor límite, ¿okay? 90 partes por billón en una hora, entonces se establece una mala calidad del aire. Cuando sube más la concentración, primera contingencia. Y ahí hacemos berrinche, ¿verdad? Porque nos limitan los vehículos y empiezan a limitar algunas fuentes de emisión. Y así. Eso es para evitar que se siga acumulando. O formando en este caso. Entonces, a ver, quedamos en que 6. Ahora déjenme introducir un concepto poco conocido. Es el aerosol atmosférico. Fíjense, qué interesante. El aerosol atmosférico es una mezcla de multicomponentes. No es un monocomponente como lo acaban de ver, que es regulado. Ozono, O3, NO2, dióxido de nitrógeno, etc. Las partículas, por ejemplo, PM10, PM2.5, vieron solamente un valor en microgramos por metro cúbico. Es un valor. Pareciera que fuera una variable, ¿no? Un monocomponente. La fase gaseosa. El aerosol está compuesto por 2 fases, una gaseosa, los que están en color son los regulados, pero también hay compuestos orgánicos volátiles. Y ella cubre una otra fase que está en fase particulada, o las partículas líquidas y sólidas inmersas en un gas forman el aerosol atmosférico. Pero de la fase particulada solo está regulada su concentración en masa, de estas dos. Las peligrosas, recordemos, que son estas. Pero es muy difícil determinar su masa, no pesan. Qué interesante. Entre más pequeñas las partículas, menos pesan, no podemos regular su concentración en masa, pero son las más tóxicas. Hay algo, hay una brecha de desconocimiento que tenemos que arreglar, porque la normatividad está basada en masa, no en composición. El orgánico volátil es un cromatograma unidimensional, y aquí está el bidimensional, y pueden ver, como acaban de explicar, que cada señal puede descomponerse en 2 o 3, o puede esconder más señales de las que aparentemente hay. Esta fracción me refiero solamente a estos orgánicos volátiles, y ninguno de ellos en la normatividad, al menos mexicana, está normado. No todo es peligroso, pero mucho sí. Por ejemplo, benceno, tolueno, etilbenceno, gilenos, los clorados. Y este es una fracción orgánica de la PM2.5 colectado un día en 24 horas en Tlalnepantla, en el noreste. De hecho, en el noroeste. De hecho, la gente que vive en el noreste y en el noroeste están más contaminados que los que vivimos en el sur, en el suroeste. ¿Pero de qué? De partículas. ¿Qué contienen? Metales y orgánicos. En el sur estamos más contaminados, digamos, más en riesgo por el ozono, ¿ok? Y poco por partículas. O sea que al hablar de qué está contaminado o está altamente contaminado, lo que sigue es preguntar ¿de qué? Porque no todo es igual, ¿ok? Como pueden ver, cada una de estas señales representa una especie, y la única técnica que puede, digamos, distinguirlos, pues es la bidimensional. Entonces, este es un estudio que se hizo recientemente, en el 2022, está Mariana, tesis de maestría, y como pueden ver, las partículas, las PM2.5 las logramos determinar, pero el 80% de las PM2.5 es PM1, es decir, traslocan. Pueden ir hasta sangre o a cerebro, por ejemplo. Y vean ustedes cómo la composición de las PM1, la mitad de su masa son orgánicos. Esto verde es orgánico, no se ve aquí, pero es orgánico. Esto es carbono negro, y estos son inorgánicos, sulfatos, nitratos, cloruros. Y vean ustedes que al analizar el orgánico con gases masa simple, QMS, pudimos diferenciar alrededor de 90 especies por hora, con una técnica que tenemos en línea. Cada barrita que pueden ver está integrada por esta suma de compuestos. Y aquí hay 400 cromatogramas. Entonces, bueno, resultados pues. Entonces, lo que quiero llamar su atención es, los cuadros es la variable normada, la concentración de PM2.5, ¿ok? Pero ven ustedes, a la misma concentración, cómo la composición varía. Por ejemplo, aquí hay mucho alcano, mucho ácido graso, eftalatos, alcoholes, y aquí cambia su composición, se reduce, ¿ok? O sea que lo que quiere... y este análisis que están viendo aquí tan complejo, solo representa el 5% del total de esta fracción, porque la técnica así no nos permitió. Está limitada nada más el tener cromatografía de gases unidimensional. Y también, para elucidar toda la composición, necesitaríamos recurrir a otras técnicas como líquidos, por ejemplo. ¿Qué nos dice la diapositiva? Que la relación entre la composición y la concentración de las partículas no es lineal. No depende una de la otra. O sea que el valor límite normado, pues a lo mejor no es completa la información y tenemos que adicionarle información de la composición. Y que lo otro es, la concentración de PM2.5 es la única variable normada, pero la toxicidad depende de la composición, de la cual los riesgos, pues, son una función. Bueno, entonces, Espero que con este ejemplo haya quedado justificado el trabajo que voy a mostrar. Entonces aprendimos que hay contaminantes primarios que se emiten, secundarios que se forman, que respiramos aerosol atmosférico y es una mezcla de gases y partículas. Tienen efectos adversos. Los contaminantes regulados son monocomponentes, mientras que los no regulados son mezclas complejas de multicomponente en aire, así como han mostrado en fragancia, en suelo, etcétera, en aire también. Y los análisis no dirigidos deben llevarse a cabo con técnicas más poderosas en cuanto a selectividad y a sensibilidad. Muy bien, entonces, ¿cómo hacemos esto? ¿Qué hacemos? Entonces, muy rápido, les quiero comentar que colectamos la muestra en algunos puntos estratégicos, en alguna zona, en este caso, esta es el área metropolitana del Valle de México, y lo colectamos en filtros. Vean cómo queda el filtro después de 24 horas de colecta. Este es el noroeste, Tlalnepantla, Ecatepec, noreste, el centro, donde ayer andábamos comiendo, aquí está, luego acá está Ciudad Universitaria y la UAM. Y hay diferentes tipos de colectores, ¿ok? Después hacemos un tratamiento de muestra y un análisis con las técnicas convencionales de gases masas. En el laboratorio lo que hemos hecho es innovar tecnológicamente para poder determinar contaminantes sin generar otros, si no, no tiene como mucho sentido seguir haciéndolo. Entonces, con el paso del tiempo hemos, digamos, innovado desde unas técnicas muy buenas de referencia hasta técnicas por cavitación muy rápidas que utilizan de 18 horas a 10 minutos y de 300 mililitros a 10 mililitros. Y obtenemos, a ver, y esta técnica pues lo ha merecido algunas patentes tecnológicas que están a disposición de la comunidad, solamente es cuestión de colaborar. ¿Sí? La universidad no es lucrativa, es para colaborar, para apoyarlos en sus quehaceres diarios, con gusto. La técnica fue probada entonces en algunas determinaciones en estos niveles de masa para poliaromáticos, por ejemplo, en ambiente, en diésel, para organoclorados y PVDs en ambiente. Y vean ustedes, pues, digamos, la técnica es bastante eficiente, es reproducible, se validan los métodos, en fin. Entonces, son técnicas, digamos, que ahora están al alcance de todos. ¿Cuál es nuestra filosofía? Determinar contaminantes sin generar otros y pensar de manera diferente e innovadora para obtener los mismos resultados con la calidad metrológica que se requiere. Ok, ¿todo bien? ¿Sí? Voy a pasar a la segunda parte de la plática, muy rápido. Les voy a mostrar 3 casos de estudio aplicando la bidimensional. El primer caso es hace ya algunos años con Mari bueno, recién regresé con el doctor Mario en la estancia, se consiguió el equipo y el modulador que van a ver es de SOEX y se compró un FID. Y pues ojalá tuviéramos un TOF, ¿verdad? Si alguien de buena voluntad lo quiere, es bienvenido. Entonces, en este momento, pues, digamos, el interés es analizar poliaromáticos. Tienen justificación porque son ubicuos, se evaporan, pues, por combustión, algunos biogénicos, pero sobre todo es por combustión de diferentes procesos y son tóxicos. Algunos de ellos son cancerígenos, sobre todo los más pesados, los que están en fase particulada, son los peligrosos. Bueno, todo lo que hizo Mari como una buena estudiante comprometida de la Facultad de Química, hizo lo que se le señala. Y entonces ella mezcló un montón de estándares, casi 100, de todas estas familias, hizo su curva de calibración a 8 niveles y después fue encontrando el periodo de la modulación. Tanto ajustó como el periodo, como el inicio, como el pulso, que pueden ver las diferentes condiciones que hizo, y el flujo de gas a cargador y la rampa de temperatura. Este es el equipo que tenemos en el laboratorio. Tiene un segundo horno. Este es no se aprecia bien, pero esa es la primera columna a través de un loop. A través de un loop, que es este, se conecta la primera con la segunda columna y un jet enfría, el otro jet calienta y libera y la pasa al segundo horno, donde hay una cromatografía rápida de 1.5 metros, y entonces obtenemos ahora del pico no modulado a los picos modulados, a las señales moduladas, para tener la separación ortogonal. Muy rápido, esto es una separación ortogonal, no polar-polar, con hidrógeno. Usamos este modulador y aquí están las condiciones. Y para aplicar digamos, estandarización de la técnica, pues colectamos unas muestras y queremos ver si funciona, ¿no? Porque pues está padre trabajar con estándares, pero vamos a ver con las muestras. Aquí pueden ver el cromatograma unidimensional con todas las familias, y es el bidimensional. Ustedes pueden ver aquí la separación de todas estas familias, aquí, muy claramente, donde separamos alcanos, por ejemplo, etcétera, y va incrementando conforme la aromaticidad, la retención en la segunda dimensión. Y aquí lo subrayé porque este conjunto de picos los pueden ver aquí bien separados. Ok, 1, 2, 3, 4, 5. Y en esta otra región, este conjunto de picos que están aquí traslapados se pueden separar muy bien aquí. Entonces, con un feed podemos trabajar. No es como un top, lo entiendo, pero es bastante bueno. Ahora, como nuestro enfoque para la tesis era poliaromáticos, primero queríamos saber los poliaromáticos dónde estaban en esa mezcla, conocer, como comentaba el doctor Mario, primero hay que conocer cuando se trata de bidimensional. Vimos entonces los tiempos de retención en la primera dimensión y en la segunda dimensión. Los conocimos, se hizo la curva, estos son resultados con la modulación. Y luego agarramos una muestra real y la dopamos, la enriquecimos con estándares. Y nuevamente volvimos a caracterizar, como pueden ver, a cada uno de ellos. Y después analizamos la muestra, esta misma, pero sin los estándares. Y encontramos lo que ven aquí. Toda la técnica funciona bastante bien, sin mínima preparación de muestra, básicamente la extracción. Y se graduó, y ahorita está trabajando. Mari, sí. Muy bien. El segundo caso son eftalatos. ¡Wow! Esto no se ha mencionado. Pero ahora los eftalatos los tenemos por doquier, ¿cierto? Están básicamente ligados a plásticos. ¿Sí? El plástico entre más maleable sea, de un solo uso, más eftalato tiene. Y hay otros que son el bisfenol A, que están en plásticos duros. Aquí están algunos ejemplos donde pueden ustedes encontrarlos. Son las moléculas más abundantes que hay y más frecuentes y están por doquier ahora. Pues si le llama la atención a los hombres, sí, hay que tener cuidado. En general, altera el sistema, modifica el sistema endocrino. Entonces, sí, ya hay bastante evidencia sobre ello. El principal contacto con los eftalatos o la absorción en el cuerpo es oral, pero la inhalada también, y la dérmica, 3 rutas de exposición, cuidado. Y bueno, son fácilmente liberados al ambiente porque no están químicamente unidos y se han encontrado en N matrices. Déjenme recomendar algo así, un comercial de salud. No hay que colocar los plásticos, los alimentos en plástico y calentarlos en el horno de microondas. Por ejemplo, la gente acostumbra a poner las tortillas, ¿verdad? Qué rica sabe la tortilla, envueltas en plástico y luego al horno de microondas. Bueno, ahí se extrae el eftalato del plástico y entonces se introduce la tortilla. Y así los tacos de canasta, los elotes, los tacos, todo lo que vemos envuelto en plástico, pues sí, ese es algo, el atole, porque el calor extrae el eftalato del plástico. Y también al bajar el pH, también extrae. Entonces, pues nada más es una reflexión. Entonces, nuevamente se hizo el análisis. Este es una tesis de maestría de Heréndira, que está aquí con nosotros, es de química, y lo mismo, su tesis de maestría usó unos filtros que se colectaron en estas zonas, usó nuestra patente tecnológica y obtuvo los extractos orgánicos. Y algunos resultados. Vean ustedes cómo, en términos de sensibilidad, cuando no está modulado el pico, aquí hay 5 ejemplos, la señal es alrededor de 30 picoamperes. Pero cuando se modula, ganamos una sensibilidad de 10 veces. Después Heréndira, 2, 3 de la mañana, inyectando y sacando sus curvas, ¿no? Tenía un plazo para titularse, y entonces... Y como pueden ver aquí, los valores son bastante buenos, ¿no? En los picos modulados, me parece que 8 niveles, una cosa así, de calibración, etcétera, y con los límites de detección, cuantificación, y validando el método. No solamente la parte instrumental, que es muy importante, sino desde la extracción. Y vean ustedes que es bastante alta la recuperación, con coeficiente de variación en aire es bastante aceptable, de acuerdo a EPA, menos del 30%. Entonces, y a diferentes niveles de adición, o sea, buen trabajo. Esto simplemente es una representación tridimensional para que vean la separación del eftalato, porque la otra es separada por columna previamente en un clean-up, que eso es lo que nos evitamos. Está padre, ¿no? O sea, la bidimensional evita un clean-up adicional. Está bien. Y si usan un termodesorbedor, evitamos el disolvente. Y para allá vamos, allá estamos, trabajando en ello, ¿no? Pero en este momento teníamos el extracto y, bueno, Heréndira inyectó, hizo lo mismo, la parte de modulación, caracterizó bien cuáles fueron las mejores variables. Y como pueden aquí ver, identificaron muy bien los eftalatos. ¿Y cómo tenía la curva de calibración? Pues los identificó. Estos son los identificados. Usamos este compuesto como interno. Esta es la separación ortogonal en bidimensional. Y los resultados mostraron que hay eftalatos en toda la ciudad. En el aire. Expuestos diariamente a ellos. El mayoritario es el verde que ven aquí y el naranja, que representa al dietilexilftalato y al dienebutilftalato ubicuamente usados en muchos productos. Y lo que menciono, y nuevamente los del norte están fritos. Son los que más, porque digamos esto es fase particulada, entonces... y las partículas por allá pues abundan, ¿verdad? Entonces esto es su tesis, hizo algunas otras cosas interesantes, pero básicamente esos son los resultados. Ahora, ¿habrá eftalatos en el cuerpo? Entonces fíjense que se hizo un análisis, que esto lo tenemos ya que hacer con técnicas como esta, como la bidimensional, porque es bastante complicado solamente usar una dimensión. Pero en colaboración con biomédicas, con investigadores de biomédicas, ellos querían relacionar el efecto del eftalato con cáncer, por ejemplo, o con depresión. La corte que se usó fue bastante baja, pero solo fue como una idea, ¿no? Como ver si había una como correlación. Y fíjense que el primer resultado impactante fue que de las 60 mujeres con diferente estadio de cáncer que analizamos, en las 60 encontramos dietilexilftalato y dienebutilftalato, en las 60. O sea, independientemente si hay asociación o no con cáncer, está el eftalato en la sangre. Eso es lo preocupante. Y bueno, ya trataron aquí de asociarlo con, parece que potencia más que inicia, más potencia. Y también alguna cosa con desórdenes de depresión. Hay que estudiar más. Y el tercer caso es pues de la estancia con el profesor Marriott. En esa estancia tuvimos la oportunidad de trabajar juntos durante 6 meses, pero los fines de semana me iba yo a bailar, Phil, eso no sabías. Pero durante la semana en un ambiente muy, muy agradable, porque convivíamos con gente de muchos lados del mundo, y entonces se hacen ambientes muy agradables para trabajar, aprende uno mucho del estudiante, ¿no? Y bueno, pues con la guía todo el tiempo. Entonces publicamos un par de artículos y un capítulo, pero solamente voy a mostrar los artículos, porque fíjense que uno de los, digamos, no tan estudiados o no tan seguidos, ahora ya habría que ver la información actual, pero en este momento el análisis cuantitativo sí era todo un reto. Era todo un reto porque como mostró el doctor, los picos modulados, ¿verdad? Y después los softwares para poder tener toda la información sin perder área o volumen, era complicado. Entonces, ¿cómo hacíamos, pensando de una manera diferente, hacer un cuantitativo correcto de los picos modulados? Porque los que trabajamos en cromatografía sabemos que el área bajo la curva o la altura, ¿verdad? Pero de los modulados, ¿cómo? Si son muchos que pertenecen a la misma sustancia. Bueno, entonces, en lo que pensábamos eso, se nos ocurrió hacer un review. Entonces, ese es un trabajo publicado y al mismo tiempo trabajábamos y se hizo el review. En este momento, pues, se habló de conceptos como análisis cuantitativo, las diferentes técnicas, la tasa de modulación, que es un nuevo concepto que el doctor creó con datos chemométricos, y el experimento que complementó el review se hizo usando dilución isotópica para poliaromáticos. Ustedes saben que el método de dilución isotópica es de lo más exacto. Eso es muy interesante por los que quieran aplicarlo. Si quieren determinar un compuesto en particular y tienen su deuterado o el compuesto isotópicamente marcado, lo que hay que hacer es agregárselo al inicio, antes de la extracción, y entonces ese compuesto estándar va a sufrir la misma pérdida que el analito de interés, y finalmente solamente usan la relación de las áreas y obtienen el cuantitativo, el análisis, la concentración final. Hay que hacer la calibración, etcétera, pero es un método muy exacto de identificación y de cuantificación, y ese es el que empleamos aquí. Muy rápido, este es el modulado y también, y estos son los no modulados. Aquí muestro que, mañana yo creo que el doctor lo va a explicar, que los picos modulados cuando diluyen pueden estar in phase, en fase, o out phase, como que no hay una sola moda, hay dos picos en moda y aquí es solamente una, se le llama en fase y fuera de fase. Y contamos los picos, 1, 2, 3, 4, 5, etcétera, ¿ok? Y entonces pueden ver que el número 1 contribuye con un área que representa el 37% del total. Si sumamos el 1 y el 2, etcétera, etcétera, hasta lograr el 1. ¿Sí? Es porcentaje de área, digamos, explicada. Entonces les voy a mostrar solamente unos ejemplos. Tomamos estos dos como ejemplo. Este es un cancerígeno para el humano, por cierto. Y entonces, bueno, disculpen. Esta diapositiva muestra que usamos el deuterado de los poliaromáticos, pero este cromatograma es de otros. Entonces, ese es del criseno y del deuterado y el criseno, que también son policíclicos. Entonces, como pueden ver acá, esta es la área no modulada y estas son las áreas moduladas. Y la idea es sumar algunos de estos y dividirlos entre la suma de algunos de estos y jugar un poco entre la suma de algunos picos modulados contra estos dos. ¿Cuál es el objetivo? Es que el área no modulada entre el criseno y el criseno deuterado, en este caso, fue 5.3. Y esa es la referencia. Aquella suma de los picos modulados que se acercara a este número, podíamos tomarlos. Y entonces, como pueden ver, algunos cumplían, pero algunos, la mayoría, no cumplían. Y entonces, lo que se trató, el modelito fue, pues cuando tú tienes los picos modulados, agárrate el 5 y el 6 para el creceno en esas condiciones de modulación, o el 1 y el 4, el 1 y el 4, el 1 y el 2 del creceno y el 1 y el 2 del creceno estructurado, súmalos y vas a obtener lo mismo que el no modulado, pero con una mejor separación y sensibilidad. Y comparamos tanto los coeficientes de correlación de los no modulados, áreas totales, de los modulados, área total, y de algunos picos más intensos. Aquí agarramos, tomamos 2, aquí tomamos 3, y vean ustedes que estas desviaciones es con respecto al área total, y no hay mucha desviación. Y las correlaciones son buenas. Es decir, encontramos un modelo simple, que no usa, para no comprar un software súper avanzado, ya los hay, para poder hacer el cuantitativo. Es una forma simple, pensando de una manera diferente, y bueno, mostrándola. Entonces, eso originó el review y el primer artículo. Y luego, la aplicación. Agarramos material de referencia certificado, estándar, y a varios masas, vean ustedes, y aquí están las condiciones. Siempre no polar, polar. Señales no moduladas y señales moduladas. ¿Y qué hicimos? Pues agarrar en lugar de todo esto, 1, 2 o 3, de acuerdo a lo que nos señaló el modelo. Estos tres, con esos tres, y tarán, el morado, es la respuesta, digamos, de referencia, que es el material de referencia de certificado, el que viene en el certificado. Y nos tendríamos que haber acercado mucho a este valor. Y vean que, pues, digamos, para algunos, bastante bien, con el intervalo. Para algunos no. Pero eso es simplemente agarrar el material de referencia, extraerlo e inyectarlo. Y ven, bastante bien el cuantitativo. Entonces, esto originó un segundo artículo, que lo pueden verificar con gusto. Es mi grupo de trabajo, ¿sí? Bienvenida a cualquier colaboración y tesis, ¿verdad? Tenemos el bidimensional con feed y pues a ver qué pasa después. Y algo muy importante son los agradecimientos al doctor Marriott por haber aceptado venir, Phil, al ingeniero Felipe, Tiago, Lucio, Natalia, a Leco Corporation por el evento, ¿no? Todos ellos son gente muy profesional. Gracias por estar acá. Al doctor Carlos Amador de la Facultad de Química, que tuvo a bien facilitar las instalaciones, al doctor José Luz, que lo traía yo sábado y domingo preguntándole cosas y facilitó mucho el estar acá, a la doctora Alma, a la doctora Araceli, gracias Alma, Araceli, en general personal de la Facultad de Química, al doctor Jorge Zavala por facilitar las instalaciones de hoy en la tarde, que ahora voy a explicar eso, y a mi equipo de trabajo, a Beto, a Maribel, a Junuen, a Jennifer, a Joshua, a Montse, a Margarita, a Mariana, a Erika, a Ángel, a Fernando, que son todo el staff. Un aplauso para ellos. A Bárbara y al personal del ICAIC también por apoyarnos. Y finalmente, esto es algo súper importante que no se nos tiene que pasar nunca. Y es un valor que ya se está perdiendo. Pero es muy importante ser agradecido, pues de otra forma el ser humano pierde su valor. O sea, es muy importante, ¿ok? Eso es todo. Gracias.
Muchísimas gracias, doctor Omar. Muy bien. Siguiendo un poco la dinámica de las preguntas, nada más vamos a cerrar con un par de ellas. En este caso, mencionaste un poco sobre lo que es detección en aire, pero no sé si tú tengas algo sobre detección en agua y también el impacto de los microplásticos que estabas mencionando hace un momento.
Bueno, digamos, como el instituto se dedica mucho al análisis de aire, pues ese es el fuerte. Hemos hecho análisis de agua también. Actualmente tenemos un extractor de fase sólida para poder hacerlo, pero yo lo utilizo más bien como para cleanup, ¿ok? Pero digamos, sí, se puede hacer, pero el fuerte es aire. Y para microplásticos yo más bien determino, o el laboratorio determina, la composición molecular, o sea, el eftalato o el bisfenol. Hemos trabajado en esos componentes, más que el microplástico, que es la partícula sólida, que le llaman que está por debajo de 5 milímetros, no sé por qué le llaman microplástico, son 5.000 micrómetros. Pero no, esa parte no, porque son otras técnicas que se utilizan, y espectroscópicas sobre todo.
Muchas gracias. Y última pregunta. ¿Qué nos puedes decir con base en tu experiencia sobre lo que es la extracción de la muestra, la importancia que tiene la extracción de la muestra para el resto del análisis?
Sí, digamos que hay algunos parámetros fundamentales que nunca tenemos que perder de vista, que es la eficiencia en el análisis, o sea, el porcentaje de recuperación para transferir el analito de la muestra al espectrómetro de masas. O sea, ¿cómo le hacemos? ¿Ok? O al detector. Es súper importante. Y lo otro es la precisión. Siempre lo mismo, siempre lo mismo. Tal vez con no sea lo más exacto o lo menos sesgado, pero siempre el mismo valor para poder corregir. Eso es súper importante. Por lo tanto, como consecuencia, tenemos que tener un buen método analítico que incluye la extracción. Súper importante.
Pues muchísimas gracias. ¿Alguien tiene alguna pregunta que quisiera tener micrófono en mano para hacer? ¿Algún valiente? ¿No? Pues si no hay nada más, entonces nada más vamos con algunos anuncios. Doctor Omar, te pido por favor que nos apoyes con esto y nada más como último recordatorio, mañana el ciclo va a ser aquí mismo, entonces para que lo tengan en mente y aún así el doctor Omar nos da últimos anuncios.
Ok, entonces a ver, porque hay un poco de confusión, digamos, básicamente hay lunes y martes son los eventos en la mañana en este recinto, ¿sí? El lunes es la sesión que ya terminó y mañana es el curso del profesor Mario, ¿sí? De 9 a 2. Y hay otros dos eventos en la tarde, pero son en ciencias de la atmósfera. El de hoy es por invitación y para la gente que aún no ha sido invitada porque no sabía la compañía o yo, sobre el interés particular en esta técnica, ¿sí? Y que potencialmente se pudiera adquirir. Esto es para hoy en la tarde, de 4 a 6 en el instituto. Para mañana el doctor Mario nos va a hacer favor de dar una última plática y esa es de acceso libre. Es más enfocada a la parte ambiental, resaltando selectividad y sensibilidad, parámetros claves en esta tecnología para esa matriz. Son bienvenidos todos y nuevamente es en el Instituto de Ciencias de la Atmósfera y Cambio Climático de la UNAM, que está cerca del metro Universidad. De aquí a allá son 10, 15 minutos caminando, está muy bonito para caminar, hagan pierna, entonces los esperamos allá. Yo creo que, ok, cualquier pregunta de todos modos están los muchachos del staff o personal del Leco, ¿sí? Gracias por la atención, los que nos tengamos que ver en la tarde, allá los esperamos, si no, mañana a las 9 por favor. Bueno, antes, ¿sí?
Muchísimas gracias.
para los que no son de la zona, con Natalie pueden preguntar acerca de los restaurantes que están aquí alrededor. ¿Ok? Hay muchas opciones.
Perfecto, muchísimas gracias, Doc. Y yo creo que ya nada más